Good morning, everyone. Welcome to the BAR workshop, or Binary Analysis Research Workshop 2024. So my name is Jun Xu. I'm an assistant professor from the University of Utah. And my colleague, Stefan Nagy, is another co-chair for this workshop. So the BAR workshop has a pretty focused goal. The goal is to have a space, to create a space so that, binary people, binary analysis people can interact, facilitate collaboration, and also present the exciting research. So this year, we're open to traditional binary analysis topics, disassembling, decompilation, form error, dynamic instrumentation. But we also welcomed new topics, newly emerging topics in this area, AI-powered binary analysis, human-in-the-loop analysis, and also, for instance, micro-patching at the binary level. So first, I would like to give a special thanks to our program committee. Similar to previous years, we have a relatively small program committee. This year, we have 18 program committee members in total. The size is small, but if you look at the list, it's a group of people from different countries, US, UK, China, South Korea. And also, every program committee member is specialized in binary analysis. So I would like really to thank the collective efforts of reviewing papers from our PC members. My general observation is, no offense to other conferences, but our reviews are probably better than many papers in the bigger conferences. So starting this year, we considered accepting short papers, which are 6 pages. And in total this year, we received 12 submissions, 6 full papers and 6 short papers. And again, thanks to the efforts of our PC members, we eventually accepted 8 papers. The acceptance rate is about 67%. So as you can see in the chart, we accepted the same amount of papers as last year. So really, we're keeping the bar, and we're keeping the bar high. So based on the topics, we reorganized the papers, accepted the papers into 2 sessions. The first session, which happens in this morning, will pretty much focus on disassembling and form error analysis. So those papers talk about more traditional, conventional binary analysis topics. And in the afternoon, we're going to have another session, which will talk about new frontiers in binary analysis. For instance, binary analysis for fuzzing, binary analysis for multivariate analysis, and also machine learning for binary analysis. So we are very honored to be able to invite 2 keynote speakers for BAR this year. The first keynote speaker is Dr. Barton Miller from University of Wisconsin-Madison. I will skip the introduction now, because in a moment I will do that. And Dr. Miller will talk about binary code patching. And our another keynote speaker, which is Peter Lafosse, and he is here. So Peter is from the industry. Peter is the owner and co-founder of Vector 35. If you're not familiar with Vector 35, Peter is the creator of Binary Ninja. So in his talk, Peter will talk about Beyond the Bats, which tries to understand the limitations of intrinsic binary analysis. And here is a brief summary of our schedule. So after my short presentation, and we will welcome Dr. Miller for the first keynote, and then we'll have a short break. And then we're going to run session 1. In session 1, we have 4 papers. Every paper has about 20 minutes. And then we're going to take a break, and then we're going to have our lunch. Then we'll continue with another keynote from Peter, and followed up by a break. Then we'll have our second session and a conclusion with a Best Paper Award. I'm not going to tell you who win, so if you want to learn, stay here. So a brief introduction, and again, welcome to the bar workshop, and thanks very much for attending. So here you have links to our homepage and also our program. You can also use your phone to scan the barcode. We also have a Slack channel, which is a workshop bar. So if you have any questions, you have something to share, feel free to join our Slack channel. Okay. So we are a little bit ahead of our schedule, but no matter what, I'm going to move forward. So I think it's okay because now we're going to do our first keynote. And our speaker is Dr. Barton Miller. So as you can see, Dr. Miller has a long profile. He has a long list of achievements, and he has a long list of titles. I can't remember everything, so I'm going to look at my slide to introduce Dr. Miller. But before I do that, I hope to make sure, and I want to make sure Dr. Miller is on Zoom. Unfortunately, he can't join in person, so he will give a presentation over Zoom. Stefan, can you confirm?
Yeah, good morning, everyone.
Yeah, great. So now I like to give an introduction to Dr. Miller. So Dr. Miller is the Vilas Distinguished Achievement Professor at University of Wisconsin-Madison. So he's a co-PI on the trusted CINSF Cybersecurity Center of Excellence, where he leads the software assurance effort. He is a pioneer of software security in many, many aspects. I just want to highlight two things. First, he founded the field of fuzzing. So if you do fuzzing, the word of fuzzing, if I am right, was from one of the courses he taught. Another thing I want to highlight is he founded the area of dynamic binary instrumentation, and he is the creator and the founder of Dynst. So Dr. Miller is also a SCM fellow. He recently won the Jean Claudy Library Award in dependable computing for his work on fuzz testing. And Dr. Miller has a long list of titles, as I mentioned. So he was the chair of the Institute for Defense Analysis Center for Computing Science Programs Review Committee, and is a member of the U.S. National Nuclear Safety Administration, Los Alamos, and the Lawrence Livermore National Lab Cybersecurity Review Committee. And he is a member of the Los Alamos National Laboratory Computing, Communications and Network Division Review Committee. And he has been on the U.S. Secret Service Electronic Crimes Task Force. And he's currently an advisor to the Wisconsin National Guard Cyber Prevention Team. So let's welcome our speaker, Dr. Miller.
Thank you, Jun. Really appreciate that. I'm going to try to see if we're sharing screen. And can you all see my slide? Someone going to give me some feedback. But all right. So thank you, Jun, and thank you for the invitation to this to talk at this great workshop. It's and I think picking Peter as the other keynote speaker is a great choice. I've worked with the Binding Ninja folks, and they're really quite good. So and I'd like to apologize for not being able to be there in person. I'm on a remote assignment for NATO somewhere, and just couldn't escape. The guys with the guns wouldn't let me out. So there's a lot of really great work being represented at the workshops. I'm really sorry I'm going to miss some of the presentations and missed the conversations on that. And I also grew up in San Diego and went to UCSD as an undergraduate, so I'm really sorry I'm missing that as well. I've been doing work in binary code for a while, so I'm going to try to walk through some of that, and hopefully this will come out in a coherent way, and we'll see how we go. So, code patching is a pretty old technique, and I'm going to walk you through a few older portions of that. And it's really interesting if you look at the last 30 years, there have been some really significant advances bringing code patching to a really everyday, commonly used technique. What was thought to be a crazy lunatic kind of thing to do is now pretty commodity. And in the last 10 years, it's accelerated. It's been fantastic work. So I'm going to talk about some really old history, nostalgia, and as Ricky Nelson sang, memories for all I sang, I'd rather drive a truck, but we'll see how that goes. I'm going to talk about binary writing and dynamic instrumentation, which are the two poles here. I'm going to switch dynants and talk about our contributions there. I'm going to talk about a kernel version of dynants we did called kernants. There's some other stuff I'm not going to talk about, but I'll share slides and people can read about something called self-propelled instrumentation. Then I'll give a summary of a bunch of stuff that we've done in the area. So let's go on. Let's start in 1961. There was a debugger built DEC for those who remember Digital Equipment Corporation and the PDP and VAX computers, lovely systems. They had a debugger called DDT, which was the DEC debugging tape. And the tape was this stuff here, this paper tape. You'd load that in. If your program crashed, you'd go over the paper tape reader like this gentleman in the white button-down shirt, of course, with a dark tie, is loading the tape in. And this would let you actually go in and patch your program and try to continue it. And actually, DDT wasn't the first version of this program. Some folks at Lincoln Labs developed it in the Flit debugger back in '57. So the idea of going in and patching code in memory and then letting it execute goes back quite a ways. Now, I got into this in 1972. I'm a bit old, I'm sorry. This is in high school, and this is actually me at Bletchley Park. For those of you who know where Bletchley Park is, where the code breakers were. And the computer I'm leaning on is an IBM 1130. It's the computer I started programming in high school. It had all of 64K bytes of memory, and I'm actually leaning on the card reader. The computer is the thing to the right with the keyboard and console. And we were working on a basic compiler for the basic programming language, which we ultimately in high school sold to IBM, which was kind of cool for high school students. And we had a card reader, and we had boxes and boxes of cards. We had, actually, it was more than 5,000 cards because it was 5. So we had about 11,000 boxes of cards, and the card reader could only read 400 cards per minute. And so the time it took to read in the program and then to assemble it and then to link it before to run it was, could take you half an hour or more. And so if the program crashed, you didn't want to go back and figure out the bug, repunch the card. So you figured out what it was. And then we went in through this console and bit switched in. We patched in by hand the update to the code. So we left patch areas throughout the code and just little empty buffers code. And when the program, so when we needed to, we hand assembled, because we actually knew the assembly language in our head for this machine. We actually knew the binary machine code language in hex in our head. And we'd write new instructions in the patch area, and we'd overwrite a jump from the strategic place, jump to the new thing, and execute it. And this was actually much faster than doing the whole process. So this was my introduction to not very automated code patching. Okay, and that just lurked in my head for a bunch of years. And yeah, this is the kind of memory of, quiz out there, if you all know what kind of memory this is. That was the RAM for the computer. Okay, let's jump forward, a decade and a half. And Earl Killian at DEC, again, great company, introduced Pixie. Now, Pixie was a tool that did very simple instrumentation. It could, on a binary, it basically put some simple code in for basically doing counters for each basic block in the code. And it used those counters as information back to the compiler, so the compiler could say, which branches were taken, which branches are not taken, and other aspects to try to optimize the code. So this was used as a very, very simple single target thing with a single kind of instrumentation to feed back into a compiler, so the compiler could then use data from previous run to generate more efficient code execution. So we're getting our first sign of automated stuff. Now, in 1992, things kind of blew up. Srivastavan Wall at, again, DEC, built a tool called OM, which was a binary writing tool. So it took in an object file, it modified it and put out a new object file. And it turns out at the same time, I want to give credit for dynamic instrumentation. Jeff Hollingsworth, who was my PhD student at the time, and I came up with dynamic instrumentation. We came up with the idea that grab onto a program in memory, parse it out, and modify the code on the fly while the program was running. And that was and now these two efforts, Srivastavan Wall and us, we didn't know anything about each other's work. So we all sort of published, and then we also noticed each other doing the stuff. One was doing it statically on object files, and we were doing it dynamically on programs that were running. So that was where it got started. Now, we did dynamic instrumentation purely to make a performance profiling tool called Paradigm more efficient. The goal was you put some instrumentation in, you measure some high-level stuff, and you evaluate that. We had a smart expert system, if you will, that was processing the performance data on the fly. It would pull the instrumentation out and drill down. If it was too much CPU time, it'd start putting more precise instrumentation for CPU time. If it was IO time, it would pull out other instrumentation and put in more precise instrumentation for IO or synchronization or memory time. So this was all built as an intrinsic component on the Paradigm performance tools. And that's where, and we coined the term dynamic instrumentation for that. So let's look at binary writing and dynamic instrumentation. Now, there's a lot of common benefits to the two. Let's start out. So I'm preaching to the choir here. You all know binary instrumentation. You don't need the source code. If you're working pretty hard, you often don't need symbol tables, strip code, and you can instrument. And the advantage of doing it statically instead of dynamically is you can instrument the binary and hand it to somebody else and share somebody else the instrumented or modified binaries. Now the disadvantage of doing it statically is if you want to change the instrumentation, you have to reprocess the binary and relaunch it again, or reload it or something like that. There's also a subtle problem that those of you who've worked on this may understand, unless you're going through a compiler tool chain, if you're lifting into LLVM and somebody's doing it. But if you're generating your own binary, you have to generate a new binary, including the headers like ELF and dwarf and things like that, symbol tables. So it's a lot of work, not just patching the binary right, but getting all the plumbing around it right, which we've actually spent too much time. And then people have used this for performance profiling, tracing, sandboxing, simulating different instruction sets, memory debugging, checking, doing memory safety checks, code optimization. So these are all things in binary writing. Dynamic instrumentation, some similar things. You don't need the source code, obviously. You have the advantage you can change the code on the fly. So you can instrument running programs. You can grab on to attach to a running server, patch, profile it, instrument it, or even patch it. We've done hot patching. We've shown how you can do safe hot patching of a running server in some of our work. And you don't need to generate a new binary executable file, but you do need to be able to control a running process and do that safely without crashing it. So it's more complex than static rewriting because you have to deal with execution state. And if you're doing like a distributed program or multi-process program, you do need an instrumentation agent on each compute node that you're running your tool on. And again, we can do performance profiling, tracing. We've done some work with cyber forensics, memory debugging, again, dynamic code optimization. I'll tell you about it in the kernel one about how we do code optimization on the fly for that. All right. So just quick thing, binary writing. It's usually easy. Some ways it's easier to report. You amortize your parsing and instrumentation time over you generate a binary, and you can run it multiple times, instrumented one. Dynamic instrumentation, you can insert and remove things at runtime. We did something really interesting. We built a tool that did code coverage testing. So we put instrumentation into every basic block to turn on a flag, turn on a flag when that block was executed. And so we modified every basic block, and the program slowed down a lot at the beginning. But as the flags were turned on, we detected it and removed the instrumentation. So the program got really slow and sped right back up again. And the net total execution time was way faster than tools that did static instrumentation that couldn't remove the instrumentation for that. So it was a really interesting example of where dynamic instrumentation really could shine. All right, let's go on, and I want to talk. So this early rewriter, OM, which was an important tool, was the first real binary writing. And these are 2 tracks in 1992, binary writing and dynamic instrumentation. It was the first general purpose rewriter. It did require symbol tables. It couldn't handle strip code. It worked on object files, and object files like the .os before you linked them to an executable. They have a lot more information in there, and it leveraged that. It was part of a single tool chain that worked with a compiler. It did some interesting analysis and optimizations. It did live variable analysis. It did dead code elimination, and it could actually hoist code out of loop. So it did some really interesting things. It was implemented for the DEC Alpha processor, for those who remember that chip. Best CPU design ever, though when DEC got sold and eventually eaten up by Dell, that all got canceled. And there was a tracing tool that was used for debugging performance called Atom that was built on top of OM. Okay, so this was a really interesting pioneering tool. A lot of stuff that we think about now was done there. Now, as I mentioned, object file, whether you do instrumentation on object files or executables, object files have an advantage. They have a lot of relocation information, which gives you more information when you want to parse the code, and simplifies finding code when you have pointer-based calls and jumps. As you know, there's some interesting challenges of trying to make sure you parse everything and you parse exactly stuff that's really code and not code. Executables don't have this information, and so you have to work harder. But most of us who work in this field work on executables, not object files. Actually, Dynance works on both, so we like to be open-minded. Okay, so OM looked like, and this is not a totally unfamiliar thing. This is why I want to talk about, a lot of stuff we take for granted. It took the object files, converted them to an intermediate form. They were using a register transfer language as the intermediate form they hoisted it to. They did the transformations on this intermediate form. A lot of people work on LLVM intermediate form, so that idea dates back to the OM folks. And then they do transformations. They do another pass to instrument and optimize it, and they generate new object files, which you then link into your program. So there was actually a fair amount of work. At Wisconsin, Jim Laris's group was doing EEL for the Spark on Solaris. University of Washington, kind of in collaboration with Microsoft, did Etch. There was a Eel descendant at Singapore that worked on the x86, the IA32 version, 32-bit version of that. Microsoft Research put together their own rewriter called Vulkan, which was out there on their website for about 35 minutes, and they pulled it off. So, some people, we got to play with it for a little bit, but then they got rid of it. There's been a lot of really good work at Arizona on binary writing, binary code analysis, including BID and PLTO and things like that. And in Ghent, there was another version that worked on a variety of processors. So this is, as you can say, so there's a lot of interesting work that we're all. There's some specialized rewriting tools. There was a tool that was basically designed to give you performance data, especially about execution frequencies, basic blocks, and control flow edges. That was built on EEL. Arizona, as I said, there's a whole set of tools built on top of their tool framework of all the Alto, PLTO, ILTO, those are all big, and some successor tools they did with Ghent, and we can see these all, including some work on link time optimization at the binary level. All right, so that's a little background. Now, code patching. So I want to talk about two approaches to code modification. One is code patching, and the other is code caching. And there's some overlapping technologies there, but tools usually fall into one of these things. Code patching, which is what we did and a lot of other people early on did, was you directly overwrite code whenever possible. So if you need to modify a branch, somebody can just overwrite the branch with the new destination. Otherwise, you copy the code you want to instrument to a patch area. You transform the copied code by, first of all, you have to relocate it because you may have to change the code if it's not completely position independent to run the new location. Short branches may have to become long branches or more complex sequences, so you have to do some interesting stuff to relocate it. And then you have to leave space in there, kind of inflated up with gaps if you want to put instrumentation code in there when modify. And then you have to overwrite the original code with a branch. And I'll show you pictures of this if this is all too much hand waving for you. And the advantage of this is you only modify exactly the parts of the code in your program that you're going to instrument. The parts of the program you're not going to instrument are completely untouched, and they stay exactly where they are with exactly the same code sequences as previous. And so now, one of the things we do if you're going to do code patching is you want to leverage code analysis, and I'll talk about code analysis in a second. So, this requires, to do this efficiently, requires good code analysis. So if you want to, let's say, instrument the entry point of function foo, here you, the basic mechanism is you're going to jump to a code patch area, which we coined the term trampoline, which is still used by some people out there. You maybe have some instrumentation you do before the instruction or instrumentation you do after the instruction, and the relocated instruction or its modified cousin. So basically, the common question is, what happens if you can't fit a jump in the place that you want to overwrite? Because the instruction is, or the basic block, or even the whole function is too small. If you have a function whose incomplete contents are returned, and you're on an x86 family of processor, that function is exactly 1 byte long. There's very little code patching you can stick in there, except the ultimate cop-out, which is a trap, which we use as our ultimate safety net for this. Now, or the instruction just before, just after has already been patched, and you can't overwrite. So, what we do with code relocation is we take either a basic block or the whole function, and we relocate it to a patch area, and then we pump it up with NOAA think of empty space where instrumentation is going to go. And, wherever it can go between instructions, before instructions, after instruction, whatever. And then we patch a jump in to this much larger area that we relocated. And we can relocate as much stuff as we need to make enough room. So we can relocate instructions, basic blocks, for whole functions. Dynance these days defaults to relocating whole functions, though you can tweak that if you want, just for our local perspective. So there's an interesting question, which I'm going to talk about at the end of the talk, is if you're instrumenting or patching something that doesn't want to be patched and it's checking itself, how do you do that so the code can't tell that you're actually patching that? And I'll talk a little bit about that. We did some work on instrumenting malware and had to address this problem. Okay, code caching is a little different. Code caching basically goes through the program's execution, and every time it comes to a new basic block, relocates the whole basic block. Every basic block gets relocated. If there's any instrumentation that's happening, that's when the instrumentation gets inserted, and then the block ends with a jump to the next basic block. If the next basic block is already in the code cache, it just jumps to a block that's already in the code cache. Otherwise, it actually jumps to the instrumentation engine, which will relocate the next basic block and do that. So every basic block is relocated. So and is modified. So that has this overhead proportional to the number of basic blocks that are executed versus overhead that's proportional to the number of basic blocks that are instrumented. If you're instrumenting every memory reference in the program, this is pretty competitive. If you're instrumenting only selected locations in the program, then code patching will be better. This is mechanically simpler to do, though most code caching instrumenters don't leverage code analysis very much on this. They do something very simple there. And again, if any of this stuff, if your tool falls into the cracks or does something different that I'm describing, new generation, I'd love to hear about it, because I'm talking about stuff that I'm familiar with, and there's so much work out there that I'm not going to know. Okay, so let me talk a little bit about what we were working on. And when we were working with, started doing work on binary instrumentation, we were doing, at the first time, dynamic instrumentation. And this was work with Jeff Hollingsworth, the gentleman on the left. The gentleman on the right is Bruce Urban, two of my PhDs from the mid-90s, both have gone on to do great stuff. They don't look this young anymore, but then neither do I. So one of the things that we did with Dynast is we felt it was very important to have a machine-independent interface to machine-level code patching. So all of our abstractions, so you can write binary analysis tools, binary patching, all this stuff you can build on top of Dynast, and whether you're doing binary writing or dynamic instrumentation, you can do it without ever referring to a single detail of the instruction set on which you're executing. So it's all abstract. You can eventually drill down and get a platform independent instruction name or register name and things like that. But 99.99% of the time, you never have to do it. So you can actually build tools that are completely portable across code architectures. And Dynast works on x86 of various flavors, and ARM of various flavors, and Power of various flavors. So these abstract interfaces, I cannot minimize how important it is, because it really, when users start writing tools for these things, it really simplifies their life. Now, Dynast provides abstractions for on the patch code patching, and also static code patching. So we have a single interface these days for binary writing, which means you open a file and then do all your analysis and instrumentation, or you attach to a processor, start a program running, and then you analyze the code and patch it on the fly. So it's this. So building a tool with a static dynamic, or switching a tool from static to dynamic mode is really easy. And Dynast is all over the place, so you may not see it. If you ever use Red Hat System Tap tracing tool, that's a veneer over it. Cray built a bunch of tools. AMD's OmniTrace. There's a bunch of high performance computing performance tools that are built on top of our work. HPC Toolkit from Rice and Tao from Oregon. But there's a lot of, we're hidden in a lot of places that you may not see. Okay, so Dynast provides the same abstraction, same interfaces for dynamic instrumentation and for binary writing. And there's three basic components to Dynast. Code analysis, which is it's hard, and we spent a lot of time working on that. Instrumentation and code modification, and the idea of using high-level abstractions instead of instruction by instruction. Code patching is an important concept I'll talk about more. And then we have an abstract interface for program control, starting, stopping, tracking events during execution, like creating a processor thread, and doing that in a platform's way that works in various Unix versions and Windows and things like that. And of course, that last part for program control is only for the dynamic instrumentation. And scalability is a big part of Dynast. We happily work on multi-gigabyte binaries. We've worked with, the biggest ones we've seen are like some physics codes out of Los Alamos, multi-physics simulation codes, heat radiation transport codes and things like that, where the biggest one we ever saw was 5 gigabytes of Pentium code, not even the headers, just the Pentium code. And we could parse that in under 2 minutes. So that's been, and we're working on real production code. That's been a really important part of what we do. Okay, so Dynast is code analysis plus instrumentation, and one leverages the others. Now, if you look at code analysis, there's a lot of really great binary code analysis tools out there. Ghidra, IdaPro, OllyDebug, Binary Ninja, which hey, Peter will tell you more about, Angra.io. Ghidra, up until not that many years ago, was a classified project within the NSA. The name was even classified. You couldn't even mention it. Surprised the hell out of me when they declassified it. I actually have some code in the early, I can't tell you where the code is, but I have some code in binary in Ghidra. It's a very nice tool, but these are all binary analysis tools. And there are binary instrumentation tools like PIN, NVBit, Valgrind, NMRIO, and others. And I'm sure there's tools some of you have here that aren't on the list. Send me the names and I'll make sure the next time I talk about this, I mention your tool. So, but these tend to be different things. So Dynast is uncommon that it leverages binary code analysis to do its instrumentation. So it means that our instrumentation primitives are based on high-level semantics, things like functions, loops, basic blocks, jump tables. So like instrument loop entry, instrument function entry, instrument function call, instrument return, instrument the branch not taken edge on a conditional jump. That's different than instrumenting an instruction or its destination. I'll talk about that. These high-level semantic operations we think are really important, and they require good binary code analysis to do them. We leverage data flow analysis to support control flow analysis, trying to figure out where doing our jump table analysis, which is really a cool piece of code in there. By the way, Dynast is open source. Take anything you want from it. Make your tool better. By the way, Dynast is open source. Contribute to it. Make our tool better. Okay, but share or steal as you wish. Make a product out of it if you want, whatever. But we think providing, using code analysis makes can make instrumentation more efficient. So, for example, you can use control flow analysis to avoid unnecessary instrumentation points. You can use data flow analysis to avoid unnecessary register saves and restores. We do register liveness. We know at every instruction, we have a conservative safe estimate of liveness. So if we need a free register at a given instruction and we know RBX is free, we don't have to spill it. We don't have to spill a register. We can actually just use RBX, not save it or restore it. Okay. So the Dynance interface, as I said, is a machine-independent representation. The code we're going to insert at points in the program, instrumentation that if you want to count or trace or whatever it is you want to do with the code, is an abstract representation. We have this whole library of AST kinds of nodes that you can build up, including things like get effective address of this instruction, or get or give me parameter one of this function, or give me local variable one, or if you happen to have compiled with symbols, you can say you can find the name of the local variable and use that instead. Because you work in the abstract level and you almost never, ever, ever use an instruction name or a register name, you can write this instrumentation once and run it on multiple architectures. And it also hides a lot of complexity. So building simple things like a function entry exit tracer, or a tracer of like the MPI message passing library used in high performance computing, you can write very small, simple tools with this. Okay, so the code analysis. So Dynance goes through and identifies basic blocks, functions, modules, variables, and also loops, and including irreducible loops, loops with multiple entries, nested and badly nested loops. It builds a call graph, that's just the interprocedural CFG, and builds a CFG per process. I told you that's natural loop detection, and it can operate happily on strict binary code, but it opportunistically use whatever information is in the symbol table, the dynamic linking table, the export table, whatever it is, we'll pick up and use that opportunistically. We do program instrumentation, which is kind of orthogonal changes. If you just want to count or time or trace or whatever it is you want to do a binary, or you can actually do code modification if you actually want to change the execution semantics of your program. They both use the machine-independent code generator interface, and a lot of our instrumentation is based on editing the control flow graph, and I'll tell you a little bit more about that in just a minute. But we basically have an algebra defined over control flow graphs. It's closed under valid control flow graphs, which makes for a very simple way to modify programs. We have process control when you're doing dynamic instrumentation, so you can attach or create a process. You can monitor process status changes. You can get callbacks to your instrumentation code if it forks, execs, exits, creates a thread, whatever. And you can actually fire off operations on the fly, like call a function in the application program and then have it return to your instrumenter. Just call one function and return. We call that inferior RPC. We can cause it to allocate memory, which can be used for instrumentation. We can do an inferior map call to malloc and allocate a patch area and come back and things like that. So there's some cool stuff in there. So our code generation is you specify the instrumentation code you want to put in as an AST, and we have platform-independent little code generators attached to each AST node type. And Spark and MIPS, how quaint those are, but this is a little bit of so those are some of the architectures we used to work on. We don't support those architectures. We've supported a lot of dead architectures. PA RISC from HP, which we don't support anymore. There's a lot of dead computers that we worked on and now are gone. Okay, code analysis has some distinct challenges, and it is a bit of a black art. And there's some people very good at it, and I'm hoping, and Peter's going to give you another keynote right after lunch, and he's another guy, and there's a lot about code analysis, and tools like Ghidra and IDAPRO. People spend a lot of brain share on this, and this is one of the things where you can get 80% of the functionality and the first 20% of the time it takes, and getting that last 20% you'll be really old before you get it really right. It just takes forever to really build a smart, fully capable, all the cases kind of thing. And then if you want to then deal with malware, which is intentionally trying to mess you up, there's a whole nother lifetime of effort, or in the way I think it, a whole nother couple of PhDs worth of effort, because that's the unit of work I often get out of get here. Some of the things you want to do for control flow analysis is find function entry points in strip code. And this is really challenging because most binary analysis tools use some form or another of control flow traversal. Some people call it a recursive parsing. I like the term control flow traversal a little better because we actually used recursion when we first wrote it, and recursion sucks, so we don't use that anymore because it's hard to back out of recursion sensibly. So it's actually an iterative process. And when compilers do code optimization, where it used to be you could scan the code and look for a function preamble, look for stack setup, local variables, parameters, local variables, return address, and things like that. But nowadays with code optimization, compilers are throwing away a large part of the preambles, moving registers around. So we actually have some techniques of looking at code using machine learning to find function entry points in places where we can't tell if there's code or not. But this is a tricky thing. And so one of the things with function entry points are non-standard ABIs for functions. The compiler, if a function is local to a compilation unit, a .o or .o file, and it's not exported, the compiler is free to call it any way it wants and get returns any way it wants and put parameters anywhere it wants and deal with stack frames or not frames any way it wants. So that makes it challenging. Loop entries, exits, back edges are interesting, especially irreducible loops and nested loops. When we went to deal with this many years ago, we took the standard algorithms in the compiler book to parse irreducible loops, and they didn't work. So we actually had to come up with modified versions of the algorithm. Jump tables with multiple levels and complex encoding, forward indexing, backward indexing, weird strides, things like that. That's kind of a fun thing. Overlapping functions. There are functions that overlap with each other. For example, two entry points that end up going to the same common finish of the function. Compilers do that now. Overlapping instructions, where two instructions actually overlap. For example, in libc, in between the threaded and non-threaded version of libc, there's a lock prefix on some instructions, and you either jump into the second byte of that instruction for a non-locked version of that function, or you jump to the first byte. So you've got two different parsers going on that are overlapping. Malware, of course, does overlapping instructions for all sorts of more nefarious reasons. So something you have to do. And tail calls, where A calls B, B calls C, and the last thing that C is doing is returning to B, and the last thing B does is return to A. So the compiler says, I can optimize that. I'll just have C return directly to A. I'll show you a picture of that. That went by too fast. And then data flow analysis, which is a place where you can spend an enormous amount of energy. It's really hard. It's like, anything to do with pointer analysis can really be challenging. And so slicing, symbolic evaluation, liveness testing. Now, so it's a constant battle between you and the compiler that's constantly trying to make the code faster and certainly not as easy to understand. Functions are no longer contiguous in memory. They're not laid out contiguously anymore. So just crazy stuff. It gets weirder and weirder, and assumptions you build in break as you go on. So one of the things that we do is we have a high-level interface to code modification. And this turns out, and so we basically have defined an algebra over CFGs, like I mentioned. And so this is just a sample of some of the kinds of things you may end up doing. You may end up splitting basic blocks as part of your instrumentation. You may join in this basic block. You may end up cloning a basic block you may have two different places branching to the same place, and you only instrument the effect of one person branching and not the instrument the effect of somebody else branching. So you do code cloning for that. So, and there's a whole sequence. We have a whole kind of pictorial dictionary for the algebra, and there's a paper on it. And this is truly an algebra that's closed under valid control flow graphs. If you feed a valid control flow graph and use our operators, you always get a valid control flow graph. You'll never get a branch into outer space or falling off the deep end or something like that into into empty memory or something like that. Okay, I want to show you why instrumenting at the high level and not at the instruction level is important. So here's an example, and this is of something called tail call optimization. And this was popular in the Spark architecture, and then about 10 years ago blew up, and every version of new compilers is using this. So here again, so A calls B, A calls B, and then it does a return. B calls C, does a return. C does something, does a return. Well, since the last thing that B does is a return, then when C returns, you'd end up going return, return, return. So instead of doing that, the compiler is smart enough that it knows that it can return from C directly to A, and you have to and knock the stack frames down to there. So basically, instead of A calling B, B calling C, C returning to B, B returning to A, just C returns directly to A, and this works for arbitrary depth. So this is really cool. Except, let's say you want to instrument the entry and exit point of each function, which is a very, very common thing to do. Common to do for performance, for timing. There's various sandboxing uses for this. There's various debugging reasons. There's a lot of reasons why you may want to do that. And so, if you look at the binary code for this, there's no. Well, let me go back to the second. With tail call optimizations, we never execute the return from B. So if I was tracing this, you'd want to see enter A, enter B, enter C, exit B, exit A. But there's no if you instrumented the entry and exit of each of these functions, you'd miss the exit for B, and that could screw up your analysis or debugging or performance. Maybe if a timer that didn't get stopped or you tracked something wrong. So by instrumenting literally the instructions, you actually have to know that the compiler did a tail call, and then you have to actually figure out how you're going to instrument that or build your analysis smarter to deal with that. So what we have here, what we end up doing in Dynance, if you say instrument the exit point of a function, we actually detect if it's a tail call. Part of our binary analysis will detect that tail calls are present. That's a standard feature of our binary analysis. And then we de-optimize the code. We convert that code into the traditional stack frame setup, call, stack frame teardown, return. And then now when you instrument this code, so if you say instrument the exit point of B, you would automatically trigger a de-optimization. So when we copy the code to our patch area, we'd actually de-optimize the code and put in entries and exits to the function, and then you'd instrument the return value. So that's kind of cool. Okay. Instrumentation overhead. Let me show you a picture. So when you actually jump to a code trampoline, you end up seeing something that looks like this. We have to save general purpose registers, floating point registers, flags. We only save general purpose registers if they're being used. We only save floating point registers being used, flags. And then if this is multi-threaded code, we may have different data collection, and so we keep track of flags. If your instrumentation code calls back into your own program, calls back to the code that calls back to a function in your code that's instrumented, you can get into an infinite recursion there. So we have to detect that we're calling this function from code that's already from instrumentation. And then we have our code in there that load, add, and store is just the thing that you actually wanted. And then we have some restores. So this is, so there's a lot of overhead here. But we can do some interesting optimizations. For example, the x86 is not a RISC architecture, so you can increment a value directly in memory. So maybe you don't even have to save a register if you want to increment a counter in your instrumentation code. And let me show you, we can use liveness analysis to track registers used. We can skip floating point registers, saves, and restores if there's no floating point instructions. We can not save flag registers if nobody's going to use them. So if we detect that the instrumentation code doesn't contain any function calls, we don't have to do the instrumentation recursion protection. If there's no multi-threading going on, we can delimitate that. So basically, this picture here, if we're not worried about recursion from a call in the instrumentation code calling back into the program itself, we can delete that. If there's no multi-threading, we can delete that. If we're using, instead of loading, storing, and adding, we can just use increment. That may allow us to avoid register saves. And we can actually, we take advantage of whatever things we don't need to do. And actually, in many cases, this is what our total instrumentation load looks like. And these are just some numbers that show that a fully instrumented program might take 900 seconds to run when the unmodified program only took 41 seconds to run. But when we go through all these optimizations, we can get the instrumented program down to just 1 second of overhead over there. So just an example of these overhead. Okay, let me take a little diversion here and talk about another project called kernels. So kernels is dyninst for kernels, running kernels. We grab onto an unmodified commodity kernel. We did this for Solaris and we did this for Linux. When we told people we were going to grab onto running programs and patch them on the fly, they said, "You're pretty stupid." We made it work, so that's good. We told people we're going to grab onto running kernels and patch them on the fly. They said, "You're really stupid." And we actually made that work, though we really worried a lot. So it uses an interface almost identical to the dyninst API and inserts runtime code into the kernel. Does everything. It parses the kernel, so there's at runtime, instruments at runtime, so there's no recompile, reboot, or even pause. These days, you could use a virtual machine and use virtual machine introspection, but we did this before virtual machines were really a thing. You can't pause the kernel. That's called a crash. And it ran on these interesting platforms. So instrumentation praise was code splicing, which is actually just another term for code patching. We use code trampolines. And one of the cool things we built on top of it was a kernel performance monitor where we could trace stuff in the kernel. There was the kernels daemon did all the stuff that dyninst does. It would read the kernel and parse it. It allocated shared memory for putting instrumentation code in and for putting instrumentation data in. We needed to do a few things in the kernel that we couldn't do just by opening dev kmem. So we had to build our own device driver to allow us to unprotect certain things at the low level of the kernel so we could patch those. One of the fun things we did, besides building a cool performance tool on top of the kernel, was we showed that you could trace the kernel, look at its performance, decided that you could do things more efficiently and patch in a new version of the binary code and make the kernel run faster. So the idea was evolving kernels at runtime. So grab onto a running kernel, patch, instrument it. You might do things like specialization. Maybe you can decide that the kernel malloc frequently allocates 1K and 4K block and generate a specialized malloc for it. Maybe you can do constant propagation throughout the code and shrink the code down. Maybe you can do inlining. We did something called outlining, which I'll tell you about. You can also build other tools with kernels like debugging, install patches on the fly. So I want to tell you about one optimization that we did with this version of with this current, and it's something it's something that Pettis and Hansen did back in the 90s statically. They analyzed the code, they tracked which basic blocks in the code executed frequently, which ones didn't execute frequently. You put a lot of if, then, else's with error checking in your code. Those else's don't execute very frequently. They're error code. But the hot blocks, the ones that execute frequently, and the cold blocks that execute infrequently are mixed together. So you have a lot of cold blocks in the iCache taking up space that could be held by hot executing code. So they basically instrumented a program, collected its data, used that data to recompile the program and move all the hot blocks together and all the cold blocks together, just reallocate how the memory was. They call this outlining. So we decided to do that on the fly. So we can instrument a function, instrument a whole call graph in the kernel, like the TCP protocol code or the file system write code or something like that. Instrument all the basic blocks in that tree and put counters on it and say, and let that run for a little while and say which blocks are running frequently, which blocks are running infrequently. It's very bimodal. It's not a gradation. There's hot blocks and cold blocks. They're either regular code or error code. And then we can then use that to copy that code out of memory, reorganize the basic blocks, put it back into the kernel's memory and patch it in. And so let's say your code looks something like this: hot block, cold block, hot block, cold block. This is just a cartoon version, but it's not far off. What the instrumentation is going to do is, after it figures out which blocks are hot and cold, it's just going to reorder them so the hot blocks are together and the cold blocks are together. And that's kind of cool. And you're doing this on the fly while the kernel's running. And as a result of this, the kernel's going to run faster. We actually ran this. We did this. One of the studies we did this on the TCP protocol code, and we tracked the protocol code and discovered that it had a really bad iCache performance. And we figured out where the hot and cold blocks were. And in the end, when we ran this thing, our web benchmark that we ran on this host ran 7% faster just by rearranging the basic blocks in the protocol code. And this all happened automatically with no manual interventions while the kernel was running. I've got some statistics in here on, how much time we shaved off an instruction, and the instructions per cycle increased by this percent and things like that. You can look at. But what's really cool is this is a simulation map of the iCache. Before we ran on the TCP code, before we ran our code optimization. So these are the number of different blocks in the code that are contending for the same location in the iCache, which means you're getting iCache misses, which means your program's running slower. And some of them are pretty bad. The ones that are pink and orangish red color, whatever color you see, are 3 and 4 different places in the code contending for the same iCache block. When we reorganized the code, so the hot blocks and cold blocks together, this is what it looked like. This is the actual map. And it was just boom. It was just really kind of cool. So this was a cool thing we did with code patching, code analysis. And patching your kernel on the fly, this one of my students drew this, is like working the engine in your car while you're driving down the highway. And it's not as dangerous as it looks because he's got a seatbelt wrapped around his ankle. So it's pretty good. Okay. what I'm going to talk about just a quick view through some stuff, other stuff we've done with binary code patching, instrumenting interpreted code. You have to account for the efficiency, the interpret. You want to be able to look at the application the programmer wrote in their language. You want to look at the efficiency of the interpreter and the instructions. There's no place where each, let's say, bytecode instruction is in the memory of the interpreter. So there's some really interesting problems here. Tia Newhall did this as part of her dissertation, and we have to revisit it given like Perl and Python and Ruby and all these languages. We've done a lot of work on lazy evaluation to parse a really big binary. You can't keep all those parsed data structures around in memory, and you want to defer parsing until you need it. That's been an important part of our scalability. We did a few years ago with John Mellicrummy at Rice, my student Xiaozhu Meng, we figured out how to parallelize code parsing, which is now more and more people are doing that. When you're parsing a big binary, gigabytes of binary, parsing becomes a bottleneck. We've been able to get really substantial speed-ups, multi-core, with our redesign. We have a nice paper on how we did this. We parsed TensorFlow, which is 100 megabytes of x86 code in 5 seconds on a 64K Pentium chip. We've been doing a lot of work recently with instrumenting and analysis of GPU code. You have vector, SIMT, SIMD instruction sets. Control flow analysis, especially with predicate, a lot of code says there's a condition mask register which says which cores are executing this instruction. Data flow analysis with these parallel with these vector type of operations is interesting and hard to do efficiently. And instrumentation, we're trying to leverage these vector operations for efficient instrumentation. This is work in progress right now. We're doing in partnership with AMD. We did some work in binary forensics, leveraging machine learning, not leveraging machine learning to identify tool chains. We actually were the first group to be able to show you can identify programmer style just from the binary code and say different pieces of code were written by the same author. There, instrumenting malware is really hard. We built a thing called static dynamic dynast that did an iterative cycle of analyzing the code that you can find, allowing the program to execute just up to that point, detecting memory changes as the code unpacks itself or overwrites itself, and then repeating these steps. And this is dealing with packed, self-detecting modified code. Malware also tries to detect that it's being instrumented, and so we actually try to formalize those properties. When the program tries to use the PC as data, use code as data, is sensitive to the size of the address space, or has its control flow successor moved because you've instrumented. Those can there's malware that tries to detect all those things. We can actually detect them trying to detect it. We can detect these properties are violated and transform the code so it maintains these properties. Like self-checksumming code uses code as data. And if you try to patch the section as checksumming, it'll detect it. But we can change the checksumming code because we know it's referencing code as data to see the old version of the code. So I'm whizzing through this stuff. There's papers and all this stuff. I think we've gone through enough stuff. Al Spector used to be VP of engineering at IBM, said most successful technologies have low usage complexity in spite of substantial internal complexity. The old phone system, web, automobiles, these all have standard interfaces to complex systems. We like to think Dynast is one of those things. Binary code, those of you working on this, you're all working on this stuff now. This is a binary code workshop. It's so much harder than it was 10 years ago and even 30 years ago. But we can leverage the really great advances of compiler technology to make our binary code analysis instrumentation more efficient. Dynamically adaptive systems may need dynamically adaptive tools. And there's a big increase in the scale and complexity of systems that are going to push the limits of our tools. So scale is really important. And now there's GPUs, TPUs, processor and memory data flow architectures that are coming out. And how do we do binary analysis on that? Well, GPUs and TPUs, I think we have some good ideas on processor and memory data flow analysis. I don't know. One of you folks will figure that out. And I think I've talked a lot, so I'll shut up and maybe allow a few minutes for questions or comments. And I'm not there, but feel free to send me an email, talk to me, set up a Zoom session, whatever. And I apologize again for not being there in person.
Thanks a lot for the. Okay.
Yeah.
Thanks a lot for the amazing talk. I really enjoyed it, and I learned a lot. So, but we have to keep you here for a little bit longer because I believe we have many questions in this room. So there is only one Mac in this room. So if you have any questions, let me know. I will go to you. Okay.
Please identify yourself.
Oh,
if I can't,
I'm June.
I know it's June. So whoever's asking the questions, please identify yourself so I know who to credit or blame.
Yes. So.
Hi, my name is Chris Hauser from Dartmouth College. I have a quick question about the patching section of your talk. I don't know which slide that was. I haven't paid attention to that. But I was wondering, in the context of position-independent executable, how you actually, if you don't have enough room to place your patch, what do you actually do in the presence of things like ASLR, PIE executables to essentially add more code to the binary without dealing with static reassembly? It looked like you had a solution for that, but I didn't really understand what you did.
Well, are we talking dynamic or static? Because the answers are slight. I mean, if it's static, we just add more code to the executable, and so the executable gets bigger, and then we jump to that, and as long as if the code is position independent, relocating it's simpler, and ASLR doesn't really affect us because wherever we execute our position independent code will do the same thing. Dynamically.
So sorry, that was for static. Yes, static patching.
Yeah.
So
in some ways, we're position independent code, so we don't really care about ASLR because we're moving, and if the code's position independent, we don't know where it's going to go into memory, so we don't really care that it goes into a different place each time because we don't know at the beginning where it's going to go. So that all works out.
Okay, so I guess I don't really understand how you add more code to the binary. So if you add a new segment, for example, how do you know where it's going to be, like what's going to be the base address?
We just make the code segment bigger. When we read it in, we get all the memory. When we go to recreate the ELF, the code segment is just bigger.
Oh, so do you also recreate the headers and all that?
Oh yeah, we know how to recreate the headers, and we make there's so much evil in those headers because there's so many assumptions that the operating system makes when it's reading those headers that are not in the standard. Like, what are the alignment criteria for each section? Is it cache line, word, page? And it's actually all of those depending on what you're doing. So it's a little bit miserable to do this, but we get it right once and then we're done. So we actually redo the headers and the dictionary at the top so we know where all the segments are in there. And we just make the code segment bigger.
Awesome, thanks for your answer. If you have any pointers, by the way, on how you did that in Dynance, I'd be very interested to check it out.
It's in Dynance. Dynance is on GitHub. Just go to GitHub/Dynance/Dynance because there's several projects under Dynance. If you can't find it, send us email and send me an email and we'll put your pointer on the code.
Thank you.
There, it's all free. I'm a lousy business person.
Hi, Roland Yap from NUS. So my understanding is that dynamic instrumentation is generally safer than static instrumentation. Just wondering what's your, for example, safer meaning, you might not have errors and you might be more complete and so on. Just wondering what is your experience with that?
I mean, we use the same code analysis and same patching, and
I mean, if one is using the new code blocks kind of approach for dynamic binary instrumentation, then you never make a for example, you don't need to worry about disassembly.
I'm sorry. Ask that again. I'm not quite.
So
following your
with
question.
static instrumentation, you do rely on some kind of disassembly, right? But with DBI, you don't actually need any disassembly. You can just do dynamic disassembly, which is never wrong.
Well, if you're the only time, so that comes up if you're dealing with perhaps malware, where the code is intentionally overwriting itself, modifying itself. If the code never modifies itself, the code is the code.
I think many static instrumenters have problems with the Chrome binary.
Okay. I'm not sure what they're doing because we haven't had problem with it. I'd like to see. I mean, I'm not sure what assumptions they're making, and I'd have to look at that specifically because we haven't had problem instrumenting Chrome. I'll have to try it again. Maybe I'll have to eat my words. But last time we looked, we didn't have any problem with that. This was a good question. Why don't we set up an offline conversation?
Sure.
And we can talk about this longer offline because I think I'd have to have my guys try this on Chrome to see if something explodes, and maybe I'm all wrong. But I always love a challenge, so we'll try Chrome.
Hi, my name's Andreas Kellis. I'm a PhD student at Columbia University. Earlier this week at NDSS, we heard a great keynote from Herbert Boss about the historic relationship between the academic community research and the hacker community when it comes to memory corruption exploitation. I was wondering what your thoughts were on the early days of binary program analysis of this relationship between the communities and how you see that today.
Well, which hacker community are we talking about? Are we talking about the good guys or the bad guys?
Any. I'm just wondering if there was any kind of inspiration being passed between academia and... Well,
there's an enormous conversation back and forth between. I mean, one of our early papers had the title "Process Hijacking," and this was a paper we wrote in like '99 of showing how to use binary code analysis for taking control of a program. Another one of my early papers is how to defeat license checkers. So I spend various time behind the fence, and I know, and remember, Ghidra came out of the intelligence community, people who hack for a living, and so I think there's an enormous synergy between those communities. And on one hand, the hacker communities eagerly trying to use these tools to do reverse engineering, to do exploitation, and things like that. And at the same time, the binary tools community is trying to identify and help people build stronger systems. And there's a constant battle between offense and defense. And I find a vulnerability, and that's good news if I share it with people and show people how to generate better code, or show people a new technique, or use binary tools to put in defensive additions. Where the offensive people said, I can use this to find a flaw, and I don't want to tell anybody because I want to exploit that flaw for my own, hopefully, purposes for good, but maybe purposes for evil. So there's a great synergy there, and there's also a great tension there. I'm sorry I missed Lafosse talk because that sounds like a really interesting topic.
Thank you.
Hey, Manuel Egele from Boston University. Awesome talk. Thank you very much. I want to come back to the nice cartoon that you had with the bold guy fixing the engine of the car going down the highway at 100 miles per hour. So when people pay Red Hat to run Red Hat kernels, what they expect is that they do this for the expectation of the support that they get. The reason they do this is that they have some sort of indemnification if something goes wrong. So how can we convince people who do that to take up your tools? What kinds of guarantees would they have for that?
Oh, that's a really interesting question. I'll say it guarantees in the technical sense. I'll say out of the legal domain because I'm definitely not a lawyer. One of my PhD students. So Ari Tamches was my student who worked on kernels and did a great job. But then we had this idea of, well, do we want to arbitrarily allow a user to put code into the kernel? And the answer, that sounds like a really bad idea. Another one of my PhD students looked at the problem of how can we look at binary code and identify safety properties in that code? Can we tell if the code is type safe? Can we tell, so does execute the instruction in the normal order? Does it always call functions at the beginning? Does it always branch to known points? And then can we also put some, so those are mandatory safety properties. Can we put some discretionary safety properties on top of that? Two, that have to do with allocation and can we liveness? And yes, in general, you can't tell if code will terminate, but you can for many codes you can, but you can't do it in general. And so we actually built, and those of you know who Tom Reps is, one of my colleagues, and a brilliant person, founded a lot of the work on compiling, on semantic analysis, compiling. If you know the word slicing, that's attributed to him and Susan Horowitz. Tom and I supervised a student, and we ended up developing techniques for analyzing a binary and telling, you can say, is this binary fit into all the safety properties, or is it unsafe, or can't we tell? Because any static analysis can be can have that middle ground there, and where we could actually say we can actually vet code coming in to the kernel for these properties, and that would then increase your confidence to do that. And that was a really interesting piece of work.
Thanks.
We're insanely out of time, so we're going to take the last question.
Okay, sorry for speaking too long. My apologies.
Hello, I'm Sharika Kumar from Cummins. My question is around how do you ensure or assure that the patch is good? Or how do you verify that an original functionality is not broken by the patch?
Right, well, so it depends on, no, that's a good question. It depends on what your intent is. If you're using Dynance's instrumentation primitives, they're explicitly designed because you're not patching in arbitrary instructions. There is a feature, you can say, I'm up here on the tightrope without a net, okay? But if you're using the normal functionality, you're using the ASTs and things like that, you're not going to change the behavior of the program. You're basically going to add things, kind of orthogonally onto the program. If you start doing things like changing a function call, replacing a function, editing the control flow graph, you're going to generate a valid program in the sense that it makes sense, but whether it's correct by any behavior that you expect, that we can't tell. So when you're using the orthogonal primitives, the instrumentation primitives, your program should stay the same, and unless Dynance is broken. But otherwise, you're on your own. I said we did some work on safety properties of instrumentation code, but not any kind of correctness properties in that sense.
All right, thank you.
It's good PhD. If you have some ideas on that, you're working on a PhD in that area, That's great. I'd love to hear about it.
All right, Bart, one last question from me. I'm Stefan. Is there any hope for Windows binary rewriting? I was looking at Dynainstance, and I know some of the to-dos are kind of fixing up Windows-related issues, and I know the file format is significantly different than for Linux. So I'm wondering, like, do you think it's a more engineering side of things that is needed for kind of the general extension of robust rewriting to Windows, or are there other kinds of significant challenges that we have to address?
We had it working at one point in time, and it kind of bit rotted just because we didn't have anybody that wanted to fund us to keep it going. It's, the difference between a PE file and an A.out file isn't qualitatively interesting. It's just all technical details to get it right. So I think, if somebody handed me some money or somebody wanted to work on it in collaboration with us, because, we love when people, contribute stuff. If somebody wanted to work on this, or you could, in, I don't know, depends on what unit of work you're doing. If you have a really good person, and certainly less than 6 months could have the rewriting part for Windows executables file.
Awesome. Well, on behalf of the audience, thank you so much for a really insightful and wonderful keynote. Please give Professor Miller another round of applause.
And thank you, everybody. I'm really sorry about there. I'm missing some of my favorite Mexican food. We just called it food when I was growing up because it was just local and that's what we ate. And we go. Enjoy San Diego, and hope to meet some of you in person soon.
Thank you so much.
Thanks for coming back to the bar workshop. Now we're going to start the morning session. In this session, we will have 4 papers, all about binary disassembling and firmware analysis. So the first paper will talk about evaluating disassembling ground truths through dynamic analysis. So our speaker, Roland, a professor from National University of Singapore. Let's welcome our speaker.
Okay, this is Joint Work with Lambang, Yuanqing, Zheng Kai, and Zhu Hao. Okay, let's start. Okay, so I don't have to tell the audience that disassemblies are important. Okay, and they are also very useful for all kinds of things to do with, you might want to do with binaries. Okay, I should say that for this talk, we focus on automated tasks rather than uses of disassembly where you are using for reverse engineering. So the difference is that automated versus manual. Because we want to look at errors. If you are doing manual, then you can tolerate the errors because you could be using interactive disassembler or you can self-correct and so forth. In automated tasks, that may not be so simple. Okay, so what's the disassembler problem? Okay, so first of all, there are 2 ways of looking at it. One is to look at it from the theoretical angle. So unfortunately, from the theoretical perspective, disassembly is just undecidable, which means that you cannot always have a correct disassembly, in theory. And it's very hard to break something which is in theory. So, but then you might say that, oh, but that's okay, undecidable, but maybe in practice it's not a problem. Right, for the binaries you want to deal with, maybe it's not a problem. Unfortunately, disassemblers are already known to have errors. Right, and there are many studies which highlight various weaknesses with existing disassemblers. I should say that there's quite a bit of related work, mainly focused on evaluating disassemblers. Okay, and you can see that, so I won't read all the papers, but you can see that, some of them just use manual analysis, so that will not work in our context. Reusing existing disassemblers, that's a bit tricky because that's a chicken and egg problem. And then the rest tend to use the compiler toolchain. Either you use outputs, you might use debugging outputs, you might modify the compiler, you might trace the metadata, and so forth. Right? And there are many papers here. Okay, but we want to do something a bit different. I should say that what I'm describing here is actually quite simple, but a little bit surprising that at least we're not aware that it's been done. So what's our motivation? So we want to find out what kind of errors that exist in the disassembly. Right? Because I give you a binary, you disassemble it, and you know that there may be errors, but precisely what are the errors for this specific binary? Right? And then you could say, well, if you want to evaluate it, well, maybe we have an oracle. Unfortunately, as we just saw, due to undecidability, there is no such perfect oracle. Okay, and then and remember that we are looking at it in a more automated process. So why are we doing this? Well, suppose you want to, do binary CFI. So step one is that you probably need some kind of disassembly and some kind of analysis of the binary. And if your disassembly is wrong, then maybe a call or jump target is not in the disassembly. Then later on, when it comes to enforcing the CFI, of course, it's wrong because you missed it. Then when it comes to enforcing the CFI, well, the CFI enforcement says that, oh no, you're not allowed to jump there, bye, and crash. Right? And of course, that would be very bad because that's a false positive. So that's why you're in some kind of automated kind of tool chain, then you would need to have some way of coping with the errors. But of course, it depends on exactly what the task is. Okay, something which is also a little bit interesting, which we didn't know until we studied these papers, is that many of these existing evaluations, well, first of all, they use benchmarks with source code in C or C++ typically, and they modify the compiler or toolchain and so on. Well, one problem with that is that you cannot evaluate a binary-only file, which is a bit strange, because the whole point of the disassembler is to run on binaries. Okay, so of course, if you are only doing an evaluation, that's okay for a set of benchmarks. But it might not help you for specific binary. Right? And of course, because they are using these techniques, they are essentially using some kind of heuristic oracle with no guarantees. Now, that does not mean that that is not useful and that it doesn't work well and so on. Simply that there are no guarantees. So, in this work, and as I said, it's quite simple, we thought to investigate the usefulness of a sound oracle. But sound would also mean that most likely incomplete oracle. Okay, so if the oracle is sound, then is that going to be useful? Okay, so our design goal is that we have soundness, and we really want to be binary level, so we're not going to care about the compiler, the programming language, and so forth. There's no dependence on that. Right? And then, of course, there's no reliance on source code because it is going to be binary only. And we're not going to assume anything about debugging information. So so essentially, we're just going to say that we want to make sure that if we say it's an error, it is an error, so sound, and that it is binary only. So G2 to G4 is just binary only. So that seems quite reasonable set of objectives. Okay, and what's the basic idea? It's very simple, right? That if you execute an instruction, then it should be in the disassembly. So the idea is that everything which is executed should be correct. Things which are not executed, well, we don't know about that.
So anything which executes, so an instruction I executes at address A, well, then the disassembly should contain this guy. So it's intrinsically sound by this reasoning. You could prove it, but we don't go to that trouble. Okay, but of course it may be incomplete unless you have captured all instructions. The good thing is because this has a minimal requirements, you can also extend it to more difficult tasks like self-modifying code, dynamic code, and so on. Okay, we haven't done this, but you can see how to do this. Okay, so that's the basic idea. Then you might think that, you need the full instruction trace. Actually, you don't need the full instruction trace, you only need the unique instruction trace. Okay, because we only need to know certain instruction at certain address once, not twice, not 3 times, and so on. Right? And in this talk, when I say trace, I would usually mean unique instruction trace, rather than saying unique all the time. Okay, so now, in some sense, you're collecting a trace. And then you might think that, okay, that's easy, but I should just remind you that there's some efficiency considerations, that the trace collector needs to be efficient enough. Okay, so this is just an example. So, and this is only an example. Actually, this example came because a reviewer asked a question. Okay, so you could, of course, do the trace by using GDB, which is the same as if you use ptrace, roughly speaking. So I call this naive. Then if you run this on MCF from spec 2006, this is with GCC -03, we tried running it, and after 11 hours, got killed at 9 gigabytes of memory. So yeah, there's trace and there's trace. Right? If you just run baseline execution, that means just normal run, that took 7 seconds. Using our trace instrumenter, it takes 8 seconds. And you see this is only a 27K binary. Of course, the size of the binary has nothing to do with the trace. However, I should also say that because we use a unique instruction trace, then the size of the binary gives an upper bound on the size of the unique instruction trace. So unique instruction trace need not be large. Whereas if you do the full trace, it would be possibly very large. Okay, just a brief outline of the implementation because we don't have so much time. Okay, so we basically collect, and this segs with the invited talk. We basically connect the unique instruction trace by using dynamic binary instrumentation, DBI. We happen to use DynamoRio, but that's just a choice. Perhaps you could do static instrumentation as well. We haven't tried. Right, but this was good enough for us. Okay, and then we collect unique instruction traces by collecting the unique basic blocks. And that's why you get efficiency. Because the number of basic blocks is much less than the total number of instructions, typically. Okay, so there's and the optimization is that there's a fast path and a slow path. So in the fast path, you just check if the basic block is unique. That means, have I seen this basic block before? If I've seen before, done, go on. Right, just run the basic block. And this is DBI, so you're modifying the code by instrumentation. And then there's the slow path, where it's the first time you see the basic block, then you need to process the basic block, you need to log in, and so on. So that's much slower. Okay? And because you're collecting traces, then of course we can combine traces. So it's also, you can increase coverage by merging traces from different runs. So we also provide that functionality. So it might be possible for, maybe to get almost full coverage or full coverage by sufficient merging. Okay, so that's the collecting the unique instruction trace. Okay, then if you take if you want to compare against some particular disassembly, well, you can just view the disassembly as also a set of instructions. So now we have two sets, right? We have the trace set and the disassembly set. Just compare the two sets to find the errors. So as I said, it's very simple. But the whole point is that it is guaranteed to be sound. Modulo like bugs in the DBI and stuff like that, of course, right? And with I think static instrumentation, maybe harder to know about soundness, because the static instrumenter may not have a very clear soundness guarantee. Okay, so that was the basic idea. And of course, the proof in the pudding is really whether is this approach useful. Right, so we tested on various binaries, SPEC 2006 and 2017, and some other binaries. And basically, we evaluated this to answer 4 questions, Q1 to Q4. So Q1 and Q2 are basic things you might want to ask whether, how do the findings correlate with existing studies? Of course, it will not be exactly the same, right? Now, for example, we have a slightly, many of the studies are using SPEC 2006, and we have a larger set here. And we have some other programs. Also, it depends on what compiler options you used and so on. So we investigate various kinds of compiler options and so forth. Okay, there's some new, also, do we find new findings? And then Q3 and Q4 are, at least as far as we know, not quite under the existing evaluation, simply because, strangely enough, as I mentioned, they require source code and compiler toolchain and so forth. So for Q3, well, we want to evaluate, non-C, C++ binaries. In this case, we choose Fortran. We choose Fortran because SPEC already contains Fortran. Right? Sometimes people forget that SPEC has Fortran in it. And of course, the real target would be things like closed source binaries. Okay, so let's see how we go. So Q1, correlation with existing studies, right? On SPEC 2006 and 2017. So this is a preliminary work, so we have run this set of compiler flags together with whatever the defaults are on Ubuntu. Okay, this is a very busy table. But before I explain the table, sorry, I forgot a slide. Okay, never mind. So many of the existing studies essentially show something like this T column. They actually show the inverse of the T column, which is the number of errors found or the number of instructions matched by using whatever Oracle you're using, right? And that is a bit crude. So in many of the studies, I forgot, I think I somehow misplaced that slide. Or maybe it's deeper in the slide deck. So you can see that if you look at those papers, you will find that they do it not by accuracy, and the accuracy is like 99% or some number like that. In which case, you cannot necessarily see the difference between the disassemblers. Right? So we present this way to show more clearly the difference between the different disassemblers and the different compilation routes. What disassemblers do we compare? We only use open source ones. So Object Dump, Anger, Ghidra, and Radar. Okay, Ghidra was mentioned just now earlier. Did he mention any other one? I can't remember. But certainly he mentioned Ghidra. Oh, okay, Anger also. Of course, he also mentioned some commercial ones, which we didn't study. Okay, so to understand this table, the way to read this table is not, so the A, B, C, D column are not the errors. The A, B, C column are the programs with errors. And whether you're an A, B, C, or D depends on how many errors you have. Like so for an A, you have 1 to 75 errors, and so on. And you can see the Anger is doing pretty well there. So we did this presentation because I think it makes it easier to see what's going on. It's different from the presentation in most of the other papers. But maybe the objective is also a bit different. Okay, so just to explain, so for example, if we take GCC minus O0, and this is across all the spec programs now, except some of the Fortran ones, we excluded Fortran from this table, though there's covered elsewhere, is simply because some of these options don't quite work on all the Fortran programs in spec. But anyway, you can see that Anger is doing quite well for GCC minus O0 because only one program has small number of errors, and the total number of errors is 9 anyway. Right? So what's the good news? The good news, this one, the tick column is object dump, and object dump has 0 errors on pure C and C++ code, and that is similar to previous work. They may not have 0, but 99% something, whatever. Recursive disassemblers, Anger, Ghidra, Radha, they all have errors. Maybe Anger seems a bit better than the others, and Radha is a bit worse, but there actually is no strict dominance. You can't see dominance in this table, but if you look at the details, then there's no recursive disassembler here, which is strictly better than the others. So no strict dominance. Yes, Anger seems on average better. And this is probably because Anger has more heuristics being used. You can see that minus O3 is generally worse than O0, but there are exceptions, like here. Right? Clang minus O3, Radha is actually, has less error than minus O0. That might be a bit of a surprise. Right? But the O3 worse than O0, maybe you might be expecting it, but maybe not the surprise bit. Okay, so that was question 1. Then question 2, about some new findings. We found that specifically LLVM now, so Clang compiler, generates PLT code which causes errors with Anger and Radha. But not GCC. Didn't quite expect that. When you go from O3 to O3 and LTO, then it leads to significant changes in errors, some plus and some minus. So maybe better or worse. Not necessarily worse. Sometimes better, just like in this example. This one's slightly surprising. Instructions after function epilogue pattern are missed. Then this one we thought, oh, well, let's just try CET. So you compile with CET on, and then it actually improves Radha. Perhaps maybe because if you do if you have CET on, then there would be an end branch instruction at the start of the function, and that could be used to identify function start. Right? Compiler has nicely, identified the function start for you. So we are assuming that maybe Radha is doing that. We didn't check the code for Radha. So that was the Q2 summary. That's just a backup slide. Q3 and Q4. Then what about Fortran binaries? So Fortran binaries, there are still some errors, but interestingly, at least for the spec Fortran binaries, only Radha, for the pure spec Fortran binaries, only Radha is affected. What about closed source binaries? So we tried 2 closed source binary programs. One is Ra, because that's quite well known. And Tigres is actually an obfuscator. It's a source-to-source obfuscator. So we thought, and it's closed source. They specifically say that they don't want to release the source. even though it's an academic project, because it's obfuscated. So they don't want to release the source so that you won't figure out how they obfuscate. And then no errors object dump, so not surprised, which means that probably these guys don't contain any significant inline assembly data. And there were errors with recursive descent, similar to what we saw before. Okay, the final thing I want to say is that, what about object dump? So we saw object dump was working very well. So we specifically tested object dump with a very small test program. But we added an ASM sequence there, which contains both instruction and data. That sequence is actually just no-op. I mean, it's not no-op, but it's equivalent to no-op. So you can basically put this anywhere you like, without cost. Okay, and not surprising, object dump now has errors. So basically, the disassembly desynchronizes. But for some reason, anger also has errors. Because you might have thought that anger is following the control flow, right, recursive descent, that this should not pose a problem. Maybe, and then also anger has heuristics to find code gaps. So don't quite know why this is happening in anger. But Ghidra was okay for this example. It doesn't mean that it's okay in general, but for this example. Okay, and we're done. So, our objective is to find errors. What are the errors in a selected binary? And it should really be closed source. We don't want to have any reliance on any compiler, two-chain compiler version, programming language, blah, blah, blah. And we have used a soundness oracle. It's very simple, but we see that we get interesting results. And of course, it is more robust. But of course, the minus is that you do lose completeness. But there's a general trade-off anyway. Okay, so we think that this may help in more automated workflows with binaries. And of course, you can complement existing evaluations. And you can do much more as well. That's it. Thank you.
Thanks very much for the nice talk. We probably only have time for one question. See any questions from the audience?
Hi, thanks for the talk. Florian Hofhammer from EPFL. Do you have an intuition where the errors you're observing in this assembly are coming from? Is this mainly due to variable instruction lengths on x86, or where are the different tools actually failing?
Well, it's a bit troublesome to check all this. Right?
Yeah, of course. Not everything manually, but like as an intuition, or maybe you looked at some examples?
Based on some checks, I think it's really due to the heuristics getting confused. Because the plus of using heuristics is that it can do, because the problem with recursive descent is actually incompleteness. And the plus of heuristics is that they can give you more completeness, and the minus is that you can get garbage. And I think it's mostly that. So for example, right, why is anger having errors? Because if you're following the control flow, right, the fact that we have some data there should not bother you because we jump around the data anyway.
Okay, thank you.
Yeah, by the way, I'm the author of the ASOK.
Yes,
so
yes.
Problem is the heuristics. So let's thank our speaker again.
Oh, you have a question?
I'm sorry?
Do you have a question?
Let's talk offline.
Okay.
Thank you. So now let's welcome our second paper. Let's wait a little bit for our speaker, Florian from the EPFL, to set up everything. So the paper title is Performant, Flexible, and Accurate Rehosting While Transplantation. So let's give our speaker maybe 20 seconds.
I just have HDMI, yeah, that should be fine. No. My HDMI shows that a display is connected and I'm showing it. Ah, yeah, here we go. Perfect. Cool. So I've already briefly presented myself, but let's get there again. My name is Florian. I'm from EPFL, and today I'm going to talk about embedded firmware, bare metal microcontroller, embedded firmware rehosting via transplantation. And to start off this presentation, I'd like to ask a quick question. Who in here has already worked with bare metal microcontroller firmware? Well, those are at least a few hands. Great. So if you're anything like me and you're writing code for bare metal microcontrollers, you're not doing it right the first time you try, and you'll inevitably need to somehow debug your firmware. If you're also anything like me, you've at some point cursed at the hardware debugging interfaces, at the tooling that is available, at potentially limited emulators. And there is one thing we can do about that, and that's basically what I'm going to talk about today. So just imagine you could use your normal user space GDB and debug the firmware in a user space process instead of on the hardware or in an emulator. So with that use case or idea out of the way, I'll go over the key insight to our approach. So on the left, we see a microcontroller-based system that runs an ARM Cortex-M microcontroller and uses the thumb2 instruction set on this bare metal microcontroller. On the right, we have a honeycomb board based on some ARM Cortex A72 cores that runs full-blown Linux and can also execute the thumb2 instruction set in the Linux user space. Our key insight here is that those two instruction set implementations are similar enough that you can execute the majority of the instructions in a bare metal firmware natively in a Linux user space process. But there is a caveat because, as I just said, the majority of instructions and similar enough. There are still some challenges that we need to take care of. And this is basically what we do with transplantation. The idea is that we take the bare metal firmware and put it into a Linux user space process where we execute it natively, but we need to take care of some small adjustments to make sure that it actually executes correctly. So in our prototype implementation that we titled Surgeon, we actually implemented this idea of transplantation. We focused on ARM Cortex-M to ARM Cortex-A transplantation, but the main idea is not limited to this ARM implementation. In a first step, we processed the existing binary firmware to take care of the discrepancies I already mentioned. And in a second step, we load it into our runtime in a Linux user space process and execute it natively. One important thing to note here is that binary firmware, of course, has different I/O functionality than your normal user space process, whereas you just have your syscalls for I/O in your user space process. In a binary firmware, you interact directly with the peripherals. In order to take care of that, we fall back to hardware abstraction layer emulation, which was introduced by Hallucinator a few years ago to emulate corresponding peripheral accesses. But that's not our main contribution. This is just what we use here for taking care of peripheral accesses. So in the first step, in the static binary rewriting step, we insert branches to the hardware abstraction layer emulation code into the firmware, basically redirecting control flow from the hardware abstraction layer functions in the firmware to our emulation code in order to take care of potential peripheral accesses. Afterwards, we take care of the potential discrepancies between the two implementations of the thumb2 instruction set to ensure that the firmware actually executes with the intended application logic semantically correct in our user space process. And last but not least, our approach also allows to introduce use case specific instrumentation. One use case, as I briefly mentioned in the introduction, would be to just use our system for debugging, for which you don't need specific instrumentation. But I'll go over another use case later on in the presentation, and there this is absolutely crucial. So to provide some examples for the three static binary rewriting steps I just mentioned, I'll start off with the peripheral emulation code. So on the left, we see the original start of a hull function, in this case for receiving data via a UART serial interface. And we will just replace the beginning of this function with an unconditional direct branch to our emulation code. So this way, everything that comes afterwards in the rewritten hull function is not executed anymore, because control flow is diverted from the hull function to our emulation code, and when our emulation code returns, it returns directly to the call side of this hull function. What is also to be noted here is that we need to ensure that we keep the layout of the firmware binary correct, so that we do not mess up any offsets in the binary that might cause issues in case there is PC relative addressing used in the binary, which is actually very common. The second thing is we need to address potential semantic differences. So I would like to stress here that those two examples I'm showing here are just examples, because they allow to show what we need to take care of, but there are also other things we handle in our system. Both on ARM Cortex-M and on ARM Cortex-A, the supervisor call SVC instruction causes a software interrupt, but the functionality is quite different. On ARM Cortex-M, this is typically used for entering an interrupt service routine that is used in real-time operating systems for task switching, for example. So when we have an RTOS that we want to rehost, of course, at such a point in time in the program, we would also like to branch to that interrupt service routine and do the task switch. However, if we execute an SVC instruction in a Linux user space process, this is the equivalent to a syscall instruction on x86, so we would issue random syscalls in our Linux system. One solution to this issue is either directly branching to emulation code, or if we're space limited, which is very common, we can replace the supervisor call instruction with a breakpoint, which causes a trap that in our runtime we can then handle and execute the corresponding emulation code. Another example for differences would be that on Cortex-M, the application program status register holds the common CPU flags, like the negative flag, zero flag, overflow flag, etc. Whereas on ARM Cortex-A, the corresponding machine-specific register would be the current program status register that is a superset of this APSR. And those are just some small things that we need to take care of in order to semantically correct execute the corresponding firmware. And finally, when we come to use case specific instrumentation, We do that via trampolines. So on the left, we see a function that doesn't do much apart from loading a constant into register R0 and then returning from the function. But highlighted in this red box is PC relative addressing, because this constant at the end of the function is addressed via this argument to the instruction. And this way, we cannot just replace such a PC relative addressed instruction with a branch to the trampoline, and we need to fall back to actually identifying an instruction or multiple instructions in the corresponding basic block that we can, without problems, relocate into our trampoline. So when we identify such an instruction, we replace it by a direct branch into our trampoline, where we add instrumentation, execute the original instruction, the relocated instruction, and if necessary, branch back to the original code location. In the second step in our runtime, we mimic the microcontroller's physical address space in our Linux user space process's virtual address space, so that any potentially hard-coded addresses in the firmware binary resolve to the intended location. Our runtime contains the emulation code for the peripheral emulation, for the hardware abstraction layer-based emulation, and optionally, we also include an embedded Python interpreter in our runtime, which allows us to reuse emulation code for the hardware abstraction layer that was already written by the original hallucinator authors who introduced this idea of hardware abstraction layer-based peripheral emulation. This allows an analyst who wants to use our system to quickly prototype the emulation code, but if performance or speed is absolutely crucial, the option is also to implement this emulation code natively and link it into our runtime. So a quick overview of how this system would then execute in a Linux user space process is that at the beginning, our loader just takes the rewritten firmware and the trampoline code and loads it into the address space of this runtime process, then hands over control to the firmware's designated entry point, and from this point on, the firmware executes natively in this Linux user space process. Wherever necessary, the firmware branches back and forth between the trampolines with instrumentation. For peripherals, of course, for peripheral accesses, while the hardware abstraction layer branches back and forth between the emulation code and the application logic in the firmware. And the same if we use the same thing if we use the Python-based peripheral emulation. The firmware can also branch to the corresponding interpreter, which then loads in the Python scripts that emulate the peripheral accesses. With this execution model, we achieve that the firmware that the bare metal firmware that we've taken in the beginning, pre-processed in our binary rewriter and then loaded into this process, executes natively in the Linux user space process at native speeds. So I already mentioned debugging as one potential use case. A second use case that we evaluated was fuzzing. This is also where the use case specific instrumentation plays a role. So for fuzzing, we took the data set of P2IM firmwares, that was introduced in the P2IM paper, and we evaluated our prototype implementation against fuzzware and P2IM. We ran the emulated code because P2M and fuzzware are based on QEMU and Unicorn respectively. We ran the emulated code on Intel Xeon CPUs and our native code on the Honeycomb board that I showed earlier on, which is based on 16 Cortex A72 cores. What is interesting to mention here is that the clock frequencies of those CPUs are fundamentally different, and also the corresponding power consumption of those systems when running a full-blown fuzzing campaign. So the first thing that we see is when we look at the execution speeds we achieve with the system is that when we run everything in an emulated manner, also our system, because it's a user space process, we can just wrap it in QEMU user, then the execution speeds are very, very similar. This becomes a lot more interesting if we actually run our code natively on the Honeycomb board. Despite the lower clock frequency, lower power consumption, we get the 3.5 to 4x speed up. Of course, when we look at fuzzing, we also want to look at coverage that we achieve in coverage-guided graybox fuzzing. And in this example, we see that with our system, we achieve higher coverage than P2IM, but lower than fuzzware, which doesn't look that good in the first place unless we consider that fuzzware and P2M are both MMO-based systems. They model peripherals on an MMO level and therefore also cover the hardware abstraction layer that we do not include in our coverage because, well, given that we redirect to the emulation code, we do not execute anything below the hardware abstraction layer. We're already better than P2M despite this fact, so let's just look at fuzzware for a comparison. If we actually deduct all the code that is below the hardware abstraction layer from the coverage that fuzzware achieves, we also can achieve better coverage than fuzzware. That being said, I'd like to conclude my talk with our cross-device class transplantation approach implemented in the Surgeon prototype. We can execute embedded firmware natively on high-performance CPUs, and we can apply common off-the-shelf user space tooling to embedded firmware. In our evaluation, we have used stock AFL++ for fuzzing, stock GDB for debugging, without any patches or redirections through QEMU or any other tooling. Our code is available on GitHub, and I'm happy to take questions. Thank you very much.
Very cool work. Thank you. Let's see if we got any questions in this room.
Just a basic question. So if there's memory RAM I/O, I'm not quite sure how you can do the emulation.
So yeah, we have the similar limitation to the original hallucinator paper. The firmware we can analyze with our HAL-based peripheral emulation requires the use of a hardware abstraction layer to a certain degree. So we need to be able to identify this hardware abstraction layer so that we can intercept the calls to anything below and emulate the peripheral accesses.
To get the hardware abstraction layer, you need to know how to create it, right?
We don't know how to we don't need to know how to create the hardware abstraction layer because the hardware abstraction layer code is typically provided by vendors such as STM, NXP, Nordic Semiconductor.
They provide it. Okay.
I hope that answers your question.
And just a quick question, right? You could run on a high-end CPU with gazillion cores, and then you could be a lot faster, perhaps. Yeah.
So in our we've ran our evaluation on those Honeycomb boards that I briefly mentioned, which are based on Cortex A72 cores. Those are the cores that are also used in a Raspberry Pi 4, for example. I haven't run my full-blown evaluation on other systems, but just to test it out, I've also used an Ampere Ultra VM in, I think it was the Oracle Cloud, for an experiment once to see whether that would be even faster. And yeah, I got another roughly 2-3x speed up there. So there is still quite some potential depending on the CPU you choose, obviously.
We can take one more question.
I'm curious about like how many of these devices that you've actually been able to like transplant, and like how long does it take to do that transplantation?
So by devices, you're referring to firmware images?
Yes.
Okay. So in our evaluation and implementation, we've mainly focused on the P2M dataset, which is only 10 firmware. I've shown one example for the fuzzing campaign here. There is some manual effort involved because you need to write the corresponding hardware abstraction layer emulation code and identify the entry points to the hardware abstraction layer in the firmware images so that you can then instrument those accordingly and redirect to the emulation code. The emulation code, once it's written for a hardware abstraction layer, is reusable across firmware images. So I already mentioned that we used the STM32 HAL from ST, and we could reuse this across a bunch of the firmware images in our data set. But actually identifying the entry points to the hardware abstraction layer and instrumenting this is a manual effort that needs to be done for each firmware image anew, unfortunately. So this is the basically trade-off you have between the hardware abstraction layer based emulation and MMO based emulation.
And was this work funded?
Yes, so I don't have the corresponding grant numbers or anything here, but I'm a PhD student at EPFL, and this was funded by the grants that our labs has.
I'd like to talk with you after.
Okay, cool.
Yeah. Let's thank our speaker again.
Thank you very much.
So now let's give a few seconds for our third speaker, Yannis. I say your name correctly, from Boston University. So in this paper, Yannis is going to talk about firm diff, improving the configuration of Linux kernels geared toward firmware rehosting.
I think so. Why doesn't it? Oh, okay, great. Thank you for the introduction. Today I'll be presenting firmdiff, a framework for improving the configuration of Linux kernels that are used in firmware rehosting. I have a feeling that everyone here knows about IoT. Pretty much these devices are everywhere nowadays. And if you know about them, you probably also know that IoT is notorious about its numerous security issues. In the past, we've seen the famous Mirai botnet attack, which brought down high-profile websites like Twitter and Netflix. And unfortunately, that was not an isolated incident because we constantly find new attacks that involve these devices. So we have to move quickly and secure these devices to basically protect them from new attacks in the future. Fortunately, when it comes to the Linux-based IoT firmware that runs in these devices, there's a lot of prior work that analyzes either a user-level aspect of it or the kernel-level aspect of it. For this specific work, we'll focus on the kernel-level aspect and specifically on the IoT kernel modules that are within firmware images. Now, to analyze these kernel modules, we have to first load them within a custom Linux kernel and then expose them to dynamic analysis. However, in order to do that, we have to make sure that the configuration between the IoT kernel modules and the custom kernel that we're going to load them into is consistent. Unfortunately, since the IoT kernel modules are in binary form, they cannot be modified, so all the instrumentation and configuration must happen on the kernel side. Now, FirmSolo is a Linux-based firmware hosting system that was published recently and does exactly that. It basically automatically builds kernels that can load the IoT kernel modules within firmware images and then expose them to dynamic analysis. Now, this system also implements a very important feature which addresses specific kernel module crashes that happen during emulation. And these crashes have to do with misaligned data structures getting accessed by these kernel modules while they're executing. Now, let's talk a little bit more about these misaligned data structures to understand what they are by looking at a very simple example. Let's say that we have an IoT kernel module that tries to access the struct net device, which stores information about the network devices communicating with the kernel. And let's say that this kernel module tries to access the dev address member of net device at offset hex 200. Now, in order for that member to be at that offset, we also have to have VLAN info within net device. And to add that member manually within net device, we would have to go to the kernel's menu config and enable the VLAN option ourselves. Now, if that member was not available within net device, dev address would be incorrectly located at a different offset. Here it will be off by 4 bytes. And when the IoT kernel module tries to access that member, it will instead perform a misaligned data structure access, which might lead to a kernel module crash. So Firm Solo could actually fix the layout of data structures in cases like this one with its automated layout alignment algorithm. However, since it is an automated solution, it has some limitations. I'm not going to list all of them here, only one of the most important ones, which is that the misaligned data structures must not be modified at source code by vendors. And that's because the layout alignment algorithm can only fix the layout of data structures by toggling on and off configuration options in the kernel, and cannot detect potential modifications added by vendors regarding the layout of data structures. Now, why is that a problem? Well, if a researcher wanted to address these complex cases of misaligned data structures, they would have to spend a significant amount of engineering effort and time to find the correct combination of configuration options and manual modifications that have to be added within Firm Solo's kernels in order to align the layout of these target data structures. Now, with that in mind, we implemented FirmDiff, which is a framework that automatically compares the memory layout of data structures between binary kernel modules and highlights cases of misaligned data structures between the compared kernel modules. Now, as you can see here, FirmDiff is a two-stage analysis process. The first stage is called kernel build stage. Second stage is the binary diffing stage. And finally, based on the information about misaligned data structures provided by FirmDiff, the researcher can find the configuration options and manual modifications that have to be applied within Firm Solo's kernels in order to align the layout of these data structures. Now, ultimately, the goal with this is to load more IoT kernel modules within Firm Solo's kernels and, of course, expose them to dynamic analysis. So starting with the kernel build stage, it's very simple. Here, FirmDiff just uses Firm Solo to compile the Firm Solo kernel and kernel modules for the target firmware image. We call them FS kernel and FS kernel modules respectively. And the FS kernel modules are very important to FirmDiff, and actually they are its sole requirement, because FirmDiff needs these kernel modules to diff them with the kernel modules within the target IoT firmware. And that's exactly what happens in the binary diffing stage. Here, FirmDiff diffs the FS kernel modules with their counterparts within the IoT firmware. And the goal of this stage is to highlight cases of misaligned data structures between between the compared kernel modules. Now, in more detail, FirmDiff will first run the GDrift binary diffing framework on an FS kernel module denoted by blue here, and its counterpart IoT kernel module denoted by green. And first, we'll analyze both kernel modules with Ghidra to produce the disassembly and decompilation for all the functions within these kernel modules, and most importantly, extract the dwarf information that is embedded within the FS kernel module, again denoted by blue here. Then it will run the Ghidra version tracking tool, which is part of the Ghidra platform, and that tool is responsible for finding function matches between the compared kernel modules. And finally, FirmDiff, for each function match, it will run the variable matching algorithm, which will essentially pair the variables of a data structure type between the functions within a function match, and then we'll highlight the cases of misaligned data structures between these functions. Now, the variable matching algorithm further consists of 3 steps. In the first step, it extracts the diffuse chains for all the variables used by the functions within the function match. In the second step, it will convert these diffuse chains into instruction vectors. If you want this information, if you want more information about these two steps, you can refer to our paper. And finally, it will compare these instruction vectors using cosine similarity in the final step, which is the variable pairing step. Here the goal is to pair the variables with the highest similarity with respect to their instruction vectors. And also, at this point, firmdiff is going to propagate type information from the FS kernel module that has debugging information available to the IoT kernel module that usually doesn't. In this case, as you can see, we have a variable x, which is of type struct net device paired with variable y. And thus, variable y will be, by association, considered of struct net device as well. Finally, firmdiff is going to display information about the names and offsets of the accessed members of the variables within a variable pair. Here, as you can see on the right side of the slide, we have information that the net DevOps, preflags, and dev address members of struct net device were accessed in this case. And we also know the offsets of these members within the FS kernel module and within the IoT kernel module, respectively. Now, based on this information, the researcher can find which configuration options and source code modifications have to be applied within FirmSolo's kernels in order to align the layout of the target misaligned data structures, in this case, struct net device. So I'm going to go into a little bit more detail about that. So here I provide the output from firmdiff as a reference. And here is the modified kernel source code that is used by one of the vendors. Now, as you can see here, the modifications are denoted by bold. However, I have to state here that the researcher will not always have access to the GPL code of the target firmware image that they're analyzing, and probably won't have this code available. So let's continue. If you can see on the left side, both NetDevOps and preflags members are off by 132 bytes from their correct offset, which actually accounts to the modifications added by the vendor in their kernel source code. And also the dev address member is off by 136 bytes, which requires the VLAN option to be enabled to add the additional 4 bytes and bring that member to the correct offset. Now, here is the upstream kernel source code that is used by FirmSolo and most probably used by the researcher as well. And as you can see here, we don't have the modifications added by the vendors available in that code. So what can we do to account for that? Well, basically, we can add padding instead, which is a technique also used by prior work. Here we add 132 bytes. And we also enable the VLAN option to bring all the access members of NetDevice at their correct offset. Now here I have to clarify that the more information provided by firmdiff about the access members of the misaligned data structure, here NetDevice, for example, the more accurately and efficiently the researcher can find how many bytes they have to add and where exactly to place them, and also which configuration options they have to enable within FirmSolo's kernels in order to basically bring all these access members to their correct offset. So we analyzed firmdiff on 10 firmware images containing 148 crossing IoT kernel modules. Firmdiff actually highlighted 37 cases of misaligned data structures within the 18 kernel modules we evaluated manually, while FirmSolo only detected 12 misaligned data structures with its layout alignment algorithm. Now, based on the information provided by firmdiff, we were able to align 35 of these misaligned data structures, which also enabled us to successfully load 28 out of the previously crossing IoT kernel modules. FirmSolo, in contrast, only aligned 4 misaligned data structures and was able to load only 5 of these kernel modules. Now, for those of you who are wondering why do we still have so many kernel modules still crossing, well, the problem lies within a specific firmware image that actually contains the majority of the crossing IoT kernel modules in our data set. In this case, the module data structure, which holds information about the kernel modules being loaded into the kernel, was extensively modified by the corresponding vendor. And actually, because of these modifications, these kernel modules crashed even before getting loaded within FirmSolo's kernels. Unfortunately, we're not able to find the correct modifications to align that data structure, and thus we were not able to address these kernel module crashes because of that. So in summary, I talked about FirmDiff, a framework that compares the memory layout between kernel modules within target IoT firmware and the kernel modules produced by FirmSolo. And the information produced by FirmDiff can aid the researcher to address more complex cases of misaligned data structures and thus build more robust kernels that can load IoT kernel modules and not worry about them crashing within during the emulation, and also, of course, expose them to dynamic analysis. So our source code will be available soon at this link, and if you have any more questions about this work, you can contact me using my email. And with that, I conclude, and I'm happy to take any questions.
So very nice work, a very nice talk.
Thank you.
We got any questions from the audience?
So maybe this is a comment and not a question, because I'm not sure if you deal with this case. So suppose one has two kernel modules, not one, two.
Yes.
And they're both different, with different alignments. So it would not be possible to have, and you can have 3, 4, whatever, right? You would not be able to have a universal alignment because the alignment could clash.
Yes. So
I don't know if that's a case you consider.
Yeah. So here in this case, FirmDiff will compare open source kernel modules that are within the IoT firmware. So there's going to be a variant compiled by FirmSolo as well. Yes, there might be extensive modifications in the kernel module within the IoT firmware, but in most cases, the data structures that are going to be used by both kernel modules are going to be probably the same. So
it could just be the config options lead to incompatible addresses. That if you meet one, you will not meet the other.
I didn't understand that. Like if you enable a config option, might enable.
So one kernel module enables certain config option. Another kernel module enables conflicting kernel options, at least conflicting in terms of addresses.
Okay.
Right? So you cannot have both addresses at the same time.
Exactly, but the information provided by FirmDiff is going to give us the opportunity to refine FirmSolo's kernels and basically disable the conflicting configuration option that had a problem. Like it's going to give us enough information to find which configuration option caused the problem and then disable it or enable it.
But if you disable it, then the module may not work.
I mean, if it was not enabled in the IoT kernel module, then it shouldn't be enabled in the kernel module compiled by FirmSolo as well. We can take it offline if you want.
We can take one more question. Any other questions? I have a question.
Yes.
So besides misaligned data structures, what are the other possible problems preventing rehosting or crashing rehosting?
Oh, there are a lot of types of crashes. So the most popular one that I've seen so far is like accessing MMIO peripherals that are not mapped in there because there's no peripheral device. So when the kernel module tries to access an unmapped address, it just crashes basically. Or there's modifications in the source code that doesn't have to do by vendors that don't have to do with data structures at all, and they just modified assertion check. And because of that, because we don't have that modification in the upstream kernel source code, when we run the IoT kernel module, it goes to that check. It sees that it doesn't. It fails essentially, and then it traps and causes the kernel to crash. But yeah.
Nice to hear. Thank you. Let's thank our speaker again. Now here comes our last paper in the setting. It's kind of new. we'll have Alexander, an independent researcher, presenting the work in the with a video, and another co-author, Marius from the University of Birmingham, will then answer questions. So first, we're going to see a video. Oh, by the way, the paper talks about a generic pipeline for large-scale analysis of non-Linux firmware.
Okay, yeah. Hi, everyone. Sorry for this quite unusual setup. Alex, unfortunately, couldn't be here with us today. We still decided that he should have the opportunity to present his work. He did the heavy lifting in this project, so that's why we're here with a recording of him, and I'm happily here for the discussion and talking with you afterwards about our work. With that being said, let's get started.
Hello, everyone. My name is Alexander Balgavi, and I'm here to tell you about Firmline, a generic pipeline for large-scale analysis of non-Linux firmware. Unfortunately, I'm not able to attend the workshop in person, but I'm glad that I can at least share our research in this way remotely. So let's get right into it. The plan for this presentation is to start off with a rationale to explain why we did the research that we did, then to give you an overview of the design of Firmline, to explain how we evaluated it, and then to walk you through some of the main insights from our research. And perhaps the best place to start is with the title. So let me break it down and hopefully that way give you an introduction to our research. So first, the general domain. Why specifically non-Linux firmware? Well, there are many studies that already analyze Linux-based firmware, but that's only a part of the entire ecosystem of firmware. The rest, non-Linux-based firmware, is relatively unknown. We don't know what operating system it runs, if it even runs an operating system, but we don't know many other properties either. And so there's a potential for security issues that could have a wide impact, which is why we choose specifically non-Linux-based firmware. We do a large-scale analysis in order to assess the ecosystem from a larger number of samples. And in terms of the analysis that we could do, there are a few options. We could do dynamic analysis, where we would run the binary and then try to analyze runtime behavior. But with non-Linux-based firmware, this is quite challenging, especially at a large scale, because the stack for this firmware is unknown. There's not really a standard. We could do a hybrid type of analysis, such as symbolic execution, but in our research, we decided to go with static analysis. So we look at the binary, we try to disassemble it, and then look at the code. So the stack that's used for non-Linux-based firmware is unknown, and it's varied, which means that we can't even know the architecture, the NDNS, the base address of a sample, whether it's 32-bit, 64-bit, 16-bit, or something completely different. Previous studies in the field narrow their scope to a single architecture, or to a vendor, or to a group of vendors, but in any case, many of these properties are already known about their datasets, so it's a bit more curated in that sense. For a true large-scale analysis of non-Linux-based firmware, we cannot do this. If it's in the wild, we don't know any of these properties. So our approach has to be generic. So Firmline is a pipeline, and perhaps this is a good point to introduce the design of Firmline, which you can see in this slide. So when we receive a new file, that file passes through several steps, some of which use an external tool for analysis. The first step is preprocessing. If we receive a file in the Intel hex or ihex format, we have to convert it to a binary. When we have a binary file, we then calculate a hash of that file, and we use that hash as an identifier, which also helps us deduplicate any files that we receive. In the next step, we do some preliminary analysis. So we calculate the entropy of the file, we calculate the file size, and we search for padding. Padding is in the form of contiguous blocks of null bytes and or FF hex bytes, and we search for this padding because it may indicate an executable file. In step 3, we try to detect whether Linux is used or referenced within the sample. For this we use binwalk, and we scan for signatures that could indicate Linux, such as Linux, but also uimage, uboot, and file systems such as squashfs. In step 4, we try to detect the architecture of the sample, and for that we use CPU-rec. We take the top 2 architectures that CPU-rec reports, and then we try to verify them with the reverse engineering framework Radari 2. If Rodari2's automated analysis finds functions given an architecture from CPU-rec, then we decide that the architecture reported by CPU-rec is correct. If Rodari2's analysis finds functions for multiple architectures, then we take the architecture with the most detected functions. In step 5, we try to detect the base address of the sample, and in step 6, we do some code analysis. Now, I'll discuss these two steps in more detail in the following slides. In the last step of the pipeline, we save the results to a database, and in our implementation, we use SQLite for this. So steps 5 and 6 in the pipeline are base address detection and code analyses. For this, we narrow the scope to ARM firmware, which is in line with previous work because ARM is a leader in many domains. However, the techniques that we use for this are generic, so to extend them to other architectures, one would really only need to replace the instruction of mnemonics in code analysis, or perhaps change the initial offset for disassembly for some architectures. In code analysis, we try to detect the usage of an operating system and/or of a memory protection unit. But first, how do we resolve a base address of a sample? Well, we borrow the approach from FirmX-Ray, which was by Wen, Lin, and Zhang. In this slide here, you see two samples of assembly code. The top and the bottom are exactly the same. What the code is trying to do is to load an address into a register using the LDR instruction, and then to branch to that address, as if it were calling a function. Now, FirmX-Ray's main insight is, if a function is called via a branch, a pointer has to be loaded via a memory instruction, such as an LDR in this case. If the base address of the sample is correct, then there should be a function at whatever address is being branched to. So if you can find the addresses of all functions, which you can detect, for example, using prologs, which consist of push instructions. And then on the other side, if you can find all the addresses that are used as function pointers, then you can iterate through all the possible offsets and choose the one where the most function pointers point to valid function prologs. Now, FirmX-Ray in their approach also used string and vector table pointers, but those require knowing some properties about the firmware. For this, FirmX-Ray used SDKs from vendors which they knew had produced the firmware. Since we are trying to be generic and we don't know any properties about the firmware that we're analyzing, we skip those types of pointers here and we only use function pointers. In terms of the security analyses that we do, we try to detect the usage of an OS because the presence of an OS potentially widens the attack surface. So it's good to know if there is one. For this, we search for SVC instructions, which in ARM is sort of like a syscall. We also try to detect the usage of an MPU, a memory protection unit, which can protect regions of memory by marking them as not writable or not executable or similar. There are two ways that a sample could be using an MPU in ARM. One is the usage of a dedicated instruction. The other is trying to access memory-mapped configuration registers of the MPU, and these are at fixed memory locations for ARM Cortex-M firmware. So let's move on to the evaluation of Firmline and see how it actually performed. The evaluation that we do in our research is we first try to see how well our base address detection performs, and we compare our simplified approach with that of FirmX-Ray. This is described in more detail in the paper. Here I'll focus more on the landscape of the non-Linux firmware in our dataset. I'll give you a brief overview of that, and then I'll discuss what we found out in our security assessment of the samples in our dataset. So our dataset consists of samples from various sources. Some of them come from previous studies, some of them come from firmware repositories that are publicly available on the internet, and some come from GitHub, where we searched for files in the Intel hex format using GitHub's search functionality. Our dataset is public, it's available for everyone to look at and download, and the link to that will be in the final slide. Our dataset looks like this. There's a total of 21,755 samples, of which 248 are Linux-based and the rest are not. Most of our samples come from the Linux firmware repository. Here, just a small remark that the Linux firmware repository is not Linux-based firmware, but it is a repository of firmware blobs for use with the Linux kernel. And most of our data comes from there, but some samples come from other sources as well, for example, the FirmX-Ray dataset or the monolithic firmware collection. In terms of the architectures present in our dataset, the top architectures detected by CPU-Rec for non-Linux samples were 6502, ARM, and MMIX. In total, we detected the architecture for 16,938 samples. Of those, we confirmed the architecture with Radari 2 in 3,287 samples. Most of them were ARM, followed by Extensa, AR Compact, 8051, and then a few other architectures. Since the top confirmed architecture is ARM, the community focus in firmware analysis on ARM architectures makes sense. In this slide here, you can see the entropy of all of the files in our database. So these are not just Linux-based, but not just non-Linux-based, but these are all of our samples that we have. On the horizontal axis, you see the mean entropy, and on the vertical axis, you see the number of samples. It's apparent from this plot that the average entropy is around 0.5. And it seems that the majority of the samples are not compressed or encrypted in any way. As for our security assessment, we're looking for the usage of an MPU and the possibility of a usage of operating system abstractions. So we do two sort of analysis passes for this based on various heuristics, as I described before. We separate this into two sample sets. The first sample set, let's call it A, those are the samples which had a confirmed architecture, so it was confirmed in analysis by Radari 2. Sample set B is a superset of A, and it also includes those samples that were not confirmed by Radari 2. So for those, we take the architecture reported by CPU-Rec at sort of face value, and we just say that that is the architecture. Now, our results for this analysis for sample set A, so those where the architecture was confirmed, we have a total of 606 samples. Of those, 28 have some sort of possible usage of an MPU, and 357 may have possible usage of an operating system. In the larger sample set, in B, which is a superset of A, we have a total of 3,262 samples. Of those, 42 seem to be accessing an MPU, and 415 of them seem to be accessing some sort of operating system facility. So that's our evaluation. Let me now summarize the insights that we gained from our research about our dataset. We found that it is possible to analyze firmware without domain knowledge to some extent, although when it comes to code analysis, there are necessarily some architecture-specific things that need to be done, so those would then need to be customized per architecture. We found that for the successfully processed ARM firmware in our dataset, the base address is most often non-zero. In our dataset, around 4.62% access the memory range of an MPU, so that might indicate possible memory protection usage within those samples. And just under 60% of our dataset contains instructions to interact with an operating system, which might indicate the possible usage of an operating system within those samples. Now, of course, our research has some limitations. We rely on external tools, and not only on the correct output of those external tools, but also on the supported input. So if a tool doesn't support the architecture that we're trying to find in a sample, then we simply cannot use that tool. And by extension, then we cannot use Firmline for that. Furthermore, the pipeline has linear dependence, which means that if we get incorrect output from one step in the pipeline, then all the following steps will also have incorrect output. Our base address detection approach uses heuristics, and these are not always correct. we restrict our code analysis to ARM, but this is not prohibitive. We collect our data manually, and our analysis is quite slow, which is not ideal for a large-scale analysis, especially if we were to scale this analysis up to an even higher number of samples. So in conclusion, we find that Firmline is a useful development in automated large-scale non-Linux firmware analysis, but there is further research needed. For example, generic techniques for firmware analysis, but also in performance optimization, so speeding up our pipeline so that we can scale it up to even more samples and get an even more comprehensive overview of the ecosystem of non-Linux based firmware. And also, there should be more research in the area of data collection so that we can collect this high number of samples that we can then feed into a pipeline. So Firmline is released as open source. It'll be available, it is already available for everyone to access at this link here, or you can use this QR code to access it. This repository also contains the dataset. And if anyone is interested in following up on this research, we would be happy to collaborate. So thank you very much for listening. And I will now hand it over to Marius for the Q&A and any further discussion. Thank you.
It's a nice talk, and I would imagine the framework will be really useful for the community. So let's see if we have any questions from the audience.
I'm curious if you did any different type of analysis for non-contiguous firmware. So, like you can't, there's multiple base addresses.
Yes, so in this work we did not focus on that. We were mostly looking at blobs under the assumption that they are in a linear memory space, because otherwise it gets very quickly a little bit more difficult to understand where the different parts are mapped if there's a special firmware file format which a vendor uses, right, with small headers. So this will require a lot of additional manual effort based on the data set we're looking at, and this work was first more like let's look at the landscape out there and do a first step to further improve on that.
Any other questions?
Hey, Manuel Egele, Boston University. Awesome talk. I have a very non-technical question that I still find interesting. So it's great that you're releasing the dataset in your repository. I was wondering whether you considered any copyright limitations that the original owners might have put that would prevent you from doing that, because in the past I was given that excuse as like, yeah, we cannot show you the data because it's copyrighted.
Yes. So I'm not a lawyer, right? So I do not know the answer to that on a legal basis, and in that regard I'm happy to ask for forgiveness rather than permission. That being said, because I believe in open science, right? I think we should have open data sets and should try to make this possible. And I mean, I do understand this concern, but in this study, we focused on already somewhere released data sets and basically just combined them into one repository on one non-Linux-based firmware collection, which is larger than all the data sets we had before in that space.
If there is no other questions, I have a simple question. Do you have a plan to handle compression and encryption?
Compression encryption? No, not in this. But here also, as our scope was blob firmware, we found that most firmware is not encrypted or compressed. If we can go back very quickly to the screen, we had the.
Can I have the slides back?
Yeah, we did the entropy analysis exactly for that to understand whether we run into this problem, right? And the thing is that usually if you have encrypted or compressed firmware, you would have, I think for encryption something around, for compression something around 0.8 upwards entropy, where we do see a spike, right? So there is likely a significant amount of compressed firmware. For encrypted firmware, it doesn't seem so much, and overall in our full data set, it's still the minority, which is why we did not try to understand the different compression and encryption algorithms used here. Compression, I guess we could tackle automatically. Encryption, rather not, right? Because we idly do not have the keys unless someone screwed it up with the firmware.
Great to hear. Thank you again. Let's thank our speaker again. So that concludes the morning session. So let's have a lunch and come back at 1:30. Thank you.
Okay, I think we can get started. So it's my pleasure to introduce our second keynote speaker, Peter Lafosse. Brief bio, Peter is an industry veteran. He started his journey 18 years ago, working at Raytheon SI, finding and exploiting software vulnerabilities, as well as writing tools to the same effect and running teams as well. He's a recipient of the coveted DEF CON Black Badge for DEF CON CTF, kind of the Super Bowl of CTF, as we all know, where he was the offensive team leader. Having served his time as a defense contractor and being dissatisfied with the tools available for software reverse engineering, he and his friends co-founded Vector 35 with the aim of building the next generation of decompilation tools. 8 years later, Binary Ninja stands as one of the most highly regarded products in the reverse engineering industry. Who here has used Binary Ninja before? Show of hands. Awesome. All right, so should all be really excited for this talk. Without further ado, Peter Lafosse.
All right. Thanks for that introduction, Stefan. So, yeah, I was very honored to be asked to come here and speak, and been very inspired by all the talks so far. I've got my own background slides. We'll go a little bit further. So yeah, like I worked at SI Govs. I was VR team lead there. They've now gone through multiple acquisitions and spin-outs, and now they're a company called Nightwing as of just a few months ago. During that time, I was really focused on dynamic analysis, fuzzing, and when we were doing CTFs, it was all static analysis. So yeah, we played in DEF CON finals many times, and we don't do that anymore because we're old men and we have businesses to run. So so yeah, those are some of my claims to fame in the CTF realm. We can talk about lots of dirty tricks that we played on people there if you want later. So in 2015, me and two of my coworkers at Raytheon, one of whom I was a childhood friend, strangely enough, founded Vector 35, and where I'm currently like the CEO, CTO, CFO, like kind of everything, plus the lead product designer there. And we wanted to build better tooling for reverse engineering. Why did we do this? First, we were like super passionate about like CTFs and vulnerability research. We kind of love the field. We love the industry. We love the people involved in it, and consequently, we're also very frustrated with the existing set of tooling at the time. Just lacked usability, flexibility. The APIs were awful, and hence the overconfidence that we thought, well, we can start a company in 5 years. This is the only thing anyone is going to use. But as Bart Miller smartly pointed out earlier, you get that 80%. And we got our 80% in the first release, and we've been working on the 20% ever since then. So we're trying to provide binary analysis capabilities, decompilation that is like convenient, reliable, it's scalable, but also we're trying to run a company and release versions. So we want a marketable product, and we want something that we're going to be happy working on for years and years and years. So it needs to be maintainable, and So those are some of our goals. And so when I talk about things, I'm talking about them mainly in the terms of static analysis and decompilation. And we focus on usability and the ability to actually have a product that is going to be, that people are going to want to buy. So we're going to kind of go through the current solutions that we have, and some of these are products, some of these are just things that we've done that we think are generally useful to everyone. So first and foremost is Binary Ninja. We launched that in 2016. We launched it in the same week my first born. I was there in the hotel room, or the hospital room with my wife in labor on my laptop, pushing code. It was okay. She didn't want to talk to me anyway. Yeah, so I jokingly say I had 2 babies in 1 week, and the one was real and this one, whatever. And just Wednesday, 2 days ago, we released version 4.0 of the product, something we're super, super happy with. Here's the tool. It's you've got your standard graph disassembly, your decompilation, your graph view and overview and cross-references, all the things you guys are probably very well familiar with. We then launched, a few years later, we launched Binary Ninja Cloud. The way we built Binary Ninja was to be a library first. So it's a library that exposes C APIs that are then wrapped in Python, Rust, and C++. And so it was actually really easy we had an intern was able to put this together, an intern plus a design company. And the reason why we did this was because this was before the era of ChatGPT. We knew that machine learning was going to be critical going forward for us. And the biggest problem with this is the lack of good data sources. And so we made this free product for anyone to be able to use, upload their binaries, do analysis, name variables, name functions, set types, and do all of the standard functionality. It doesn't have any scripting or any of some of the more advanced features, but it gets the job done for a lot of people. They can solve CTF challenges or whatever with this. Later on, we launched Enterprise. This is just our collaboration server. You'd have Git-like collaboration between you and your colleagues, and you can chat, and it's really cool. And a couple of years ago, in collaboration with some of the Anger folks, we launched the Decompiler Explorer. I'm sure you guys are all familiar with Godbolt, the godbolt.org, the compiler explorer. Well, this is the opposite, and hence the name Dogbolt. And we even reached out to Hexrays, and together, us and Hexrays sponsor the hosting of the service, and we both provide licenses so that the thing can be run on the public for free for everyone. Yeah, and this is it. So you can see side by side, all of the major decompilers. There's a bunch of other ones that are available as well. And this source code is all free and open source. Obviously, it doesn't contain the binaries or licenses for Binary Ninja or Hexrace. But this is a great way to just compare side-by-side decompilation output. So most recently, in January of this year, and we haven't even really done a big marketing push on this, we launched our Sidekick product. It's still kind of like early access, but this is an AI-based reverse engineering assistant that we're going to talk a lot more about in later slides, but this is kind of it. You can see that like it allows you to get suggestions for the kinds of things that you would generally be doing manually. So I talked in the beginning about like intrinsic binary analysis. That's my title, kind of the title of my talk, and so what I'm interested for the purpose of this talk is to kind of discuss a bifurcation of the domain into two things. We're going to say there's intrinsic binary analysis, and then there's extrinsic. There's some overlap between, just like there's maybe some overlap between static and dynamic, but you'll see as we go along. So intrinsic analysis is a bottom-up. So we're going to take bytes and we're going to raise them up and model them in some way, shape, or form. So for decompilation, we're going to take the bytes, convert them to instructions, convert those instructions to an intermediate representation, iterate on the intermediate representation, and finally put out some kind of pseudo-C or something like that. And this is what Binary Ninja, IDA, Ghidra, Anger do. Symbolic execution is similar, except kind of the last step there is for the purposes of generating SMT that can be solved for reachability or whatever. All of these mechanisms are inference-based. We lack information, and we are trying to reconstruct information from the base principles. And this has some just inherent limitations. So obviously, if you've ever done decompilation, decompiled anything, all of the variable names are gone. Maybe you'll see something like a loop variable being called I or J, K, but you're not going to get much beyond that. Some of the more recent stuff, like Binary Ninja and IDA, can infer from parameter names the variable names. But the locality there is very limited. You're never going to be able to guess what the original functions or variable names truly were. Types can be recovered, but again, only limited. When we can infer the size of an integer by the register size or the memory access size, but we only know that it is we don't even know the sign of that integer until we see it being used in a comparison. Pointers, we can't tell that something's a pointer unless we heuristically guess that it's a pointer because it's within the valid range of the binary, or we see it being dereferenced. Arrays and structures, again, we have some techniques for inferring those, but they are always going to be partial solutions because there are just inherent undecidable things within both of those. And then obviously the kind of meta of the code, we're never going to be able to recover using intrinsic analysis. So we're not going to be able to determine what algorithm this thing is, what kind of, what the comments were, or high-level intent. And ultimately, if we step back and think of what decompilation is, compilation is we're taking this, let's say, a Git repo with all of the data that's in it, the Git history, the make files, the config files, the documentation. We're running that through CMake or whatever, and we're outputting a binary. If we had a perfect decompilation, it wouldn't just recover the source code. It could also recover the file structure of the files that were in the decompilation. Maybe it could recover the Git history, given enough information. Maybe it could recover make files. Like the ideal thing that we will probably never get to is the logical inverse of what the act of compilation is. So, extrinsic analysis. This, as opposed to intrinsic, is a top-down, you might say. It is the application of external sources to the binary. So some examples of this are things that you already think as part of the normal decompilation workflow, like function signature matching. So we take a known binary, and we are able to apply, a known binary with symbols. We run through it, create signatures for each of the functions in those, and then we can run those signatures against this binary with unknown functions, and we can find out what they are. We can transfer the name of the function. We can apply types based off of that. Binary Ninja has SIGKit, IDA has Lumina and Flirt, RevNG has their big match thing. VX class was something that Zynamics, BinDiff, that's actually what they got bought for by Google, was because they could do, it was essentially very useful for malware classification. Other types of extrinsic analysis, all of the machine learning that we apply on top of the binary analysis, like what we're doing with Sidekick. The type libraries, these are, you take some source, you extract all the function names, you extract all of the types, and then when you have a binary that references externals, you can match up the function name with the external name, and now you can bring in the types that are associated with that. So now it makes it a lot easier to do analysis. So bin diffing is another type of extrinsic analysis. And instead of taking a source, you're taking a different source of information, which is another version of that same binary. We can kind of combine those things to find out how the code changed over time. Variant analysis is another type of extrinsic. It's, again, like function signature matching, but with kind of some different goals and capabilities. So all of these are essentially matching-based analyses. So why do we do all this stuff? I think it's important that we step back and think about this. When you open up a file in IDA, Ghidra, Binary Ninja, you're presented with a list of functions and the main entry point if you're lucky. But your question is never, what is the main, what is the list of functions? Like, you have a goal. You have a goal to conduct vulnerability research. I want to find where there are bugs. I want to do malware analysis and figure out what classification this malware is. So I've kind of coined this term that I routinely talk with my employees about. It's reference over inference, and don't guess when you can know. We sometimes get stuck in this mode of I must infer. I must infer from base principles these higher order things, and I caution that that's not always the approach we want to take. If we can know for a fact, we should do that instead. So should we be trying to infer that there is a CVE in this binary? Well, no. We should know that it matches this other binary that has a CVE in it, and then we can look this up. Should we try to manually analyze the latest version of whatever binary you're looking at and try to figure it out? No, we actually use bin diffing for that exact purpose. We're going to reanalyze every new piece of malware. No, we're going to do some kind of variant analysis to see if we can figure out, is this a different version of that old thing? So overall, I think that this extrinsic analysis it more directly maps to what the person's end goals are, rather than the intrinsic analysis. So when where we're spending our time developing tools for people, I like to keep this in mind. So a couple of the extrinsic analysis that we're doing right now that I think is really kind of on the cutting edge is two things: source-aided analysis and integration with generative AI. And I probably should have just said AI because it's not all generative. So source-aided analysis. If you were to scan GitHub, which has been done before, you'll find that 70% plus of the files out there are duplicated. Does anybody know how much code inside of binaries is duplicated? Like, I don't think there's ever been a study conducted that has tried to kind of quantify this. One, because it's tough. It's not an easy thing. But yet we're always reanalyzing the entire binary every time and not applying any of this knowledge that might exist in just sitting there on GitHub. I can't tell you how many times we've been reverse engineering and especially when I've been helping younger new guys on the team, and I'm like, did you Google that constant? did you just Google that? And they do. And then what happens? Oh, it's RC4. Oh, no, it's, this, I'm just thinking of all the CTF things that we've done in the past. But you shouldn't be forced to Google things when the tools should be advanced enough that they can be able to detect these things. So as part of our research with STR, we've developed a tool called SourceHammer to kind of solve a lot of this. So what SourceHammer can do is it can search like thousands of source repositories and identify matches against your current binary, and then align the source code and the binary with high fidelity, and then import all of the analysis and all of the types, all of the names, all of the comments from the source code. So generative AI and AI in general, this is kind of, it's the holy grail of everything, so it might as well be the holy grail of decompilation. And it really simply solves a lot of the problems that we have with intrinsic analysis of determining intent, determining names, commenting. It's still not great at a lot of things, but this is as bad as generative AI is ever going to be, so it's going to get better very quickly. So we've been developing Sidekick. This uses our own in-house trained models that we've been training on our own data. We use open source models as well, where it makes sense, and OpenAI for a lot of the generative stuff. So I'm not going to do a live demo. I can do a live demo if anyone wants after the fact. This is Sidekick. It essentially enhances your analysis by first making suggestions for all of the variable names. It can do interprocedural analysis to recover structures and fields, and then automatically apply names to those fields. Dead store elimination, generate comments. One of the, so let's consider you had, a fully symbols for your binary. So, but you're still reverse engineering. Why are you still reverse engineering? Because you're looking for things. And so what we made is, it's the same way you look something up in a book is you use the index, right? And so we made up a thing called indexes. And what these are is, very simply, it's just a list of things. But the way that it's generated is interesting. We can use generative AI to describe the problem that the thing that you're looking for, and it will generate the code. If it screws up, it does screw up. You can modify that code and run it. And it will generate you a list. You can go through the list and say, oh, these are all for this particular CVE that I'm looking for, and then you can find what's on the list. So kind of a complement to the indexes is a thing we call the code insight map. Think of it as a contextual call graph. So it's able to take a kind of the cross product of the various indexes that you're interested in. So if you're interested in how does the path from the network get to the file I/O? So you can add an index to find all of the functions that are doing file I/O. You can add another index that are doing network I/O, and now you can display them within a single graph. It lets you say, okay, and in this one, we're also looking at the crypto. So we can see that it's going to do some SSL, and then it's going to read some files, and then it's going to write that file out to disk. And then finally, the conversational AI aspect of this is you're able to chat with your binary. You're able to ask functions. You're able to ask things about, you can see up in the top left, it has the context of what the particular function that you're viewing is, and you can now make inferences. You can ask it questions about, like, what's the third parameter to this external that I don't know about, or this even has generative capabilities built into it. So you can say, get me a list of functions ordered by cyclomatic complexity. And it will say, oh, I know, you actually want me to generate you an index. And then it will generate you an index and pop you over there, and then run the index, and then you'll have your list of functions. So that's a sidekick. But this is where we're at now. I haven't seen anything that's, I think this is like where the cutting edge is in terms of where we are in binary decompilation. But the next question is like, all right, what is next? Where are the new research fields going to be? And so this is my speculation. Intrinsic analysis first is indispensable. Don't think I'm saying intrinsic analysis is not helpful. It's amazingly helpful, and we would be nowhere without it. However, the big advances in reverse engineering and decompilation, I don't believe are going to come from better intrinsic analysis. Yes, we can improve our function start detection. There's been recent papers about that. They're great. There's been recent papers about better control flow recovery. Those papers are great. But they're not going to change how someone does their job. They're going to make how someone does their job easier. And we're really interested in, like, how do we, shape the ease in which someone gets their job done. Can we, instead of giving them an incrementally better decompilation, can we just jump them to the end and say, okay, you don't need to analyze this binary anymore. We've found the vulnerability. We've shown you that it has what the CVE is. That's where I think we're going. And this in particular makes it difficult for researchers like a lot of you here. Is I think a lot of the integration, the things that are going to make a big impact are big data related, and that usually takes a lot of money and a lot of there's a whole lot of engineering that goes into it. So. I showed you guys SourceHammer, but there's a lot that can be done with that to make source code to binary matching be a lot faster, larger data sets. We were only taking, the 1,000 most popular repositories, but there's millions of repositories out there that can be used. We need to be able to do this same thing with binaries at scale. We've got, millions of malware samples coming in every day, and yet our systems are not capable of being able to handle those. So we need to be able to provide better tooling so that when someone ultimately does have to open up a malware sample in one of these tools, they can know what are the variants on this, what is close to this thing that I'm opening. What about the next thing is automatic binary differencing. I kind of jokingly talked about could we recover the Git history? Well, if you had every intermediate version of a binary and you were able to difference every single one of them, well, and you mix in a little bit of generative AI, that's not far off from recovering the Git history of this. This would be an amazing tool for anyone that is having to reverse engineer the same, Chrome, the same iOS image over and over and over. Deeper machine learning integrations. Right now, I've seen two kind of applications of machine learning that have been interesting. I've seen neural nets for function start detection, and I've seen kind of the slathering of machine learning on the output. But I've not seen, let's say, a machine learning based control flow recovery algorithm, or perhaps improving alias analysis using machine learning. Some of these problems that are just known to be intractable we've known they're impossible to solve for decades. Machine learning is getting us to the point where we might actually be able to make some progress in those areas. I'm really interested in where this is going. Another machine machine learning thing that we can leverage, and I think this is going to be huge for firmware analysis especially, is retrieval augmented generation. So this is essentially you ask the machine learning model to first consult this PDF or this spec or this data sheet, and now do your analysis on the binary. In firmware, you'll see a lot of, it's just writing to this special register, and there's nothing special about it except in the data sheet for this particular thing, you can find out what that information is. And this is, these custom boards that there's one-offs. This is the only way we're going to be able to make any headway other than, I think this is the only way we're going to be able to make any headway is through retrieval augmented generation. Configuration files, packet captures, dynamic traces, all of these systems, all of these sources of data can be leveraged to be able to augment decompilation to, and not just decompilation, I imagine leveraging this with leveraging packet captures as well as decompilation would be amazing for protocol recovery. Talk about like recognizing which encryption algorithm it is, where the checksum is. These things are easy to do from a decompilation perspective, decompilation coupled with machine learning, at least. And using dynamic traces, we can know where, call target is of indirect calls, or where we practically, or where our value set analysis tells us it's within this giant range that doesn't help us. These dynamic traces could be able to constrain our analysis and say, actually, it's only ever 0 through 4, and now we can constrain down our analysis and make better and deeper inferences. So, in conclusion, I think what we're kind of witnessing is a convergence between the binary analysis capabilities being raised up to the level that the source code analysis tools are at. And the source code analysis tools are actually, I've got friends who are like, I want Binary Ninja, but for source code. And they're building those things. So ultimately, the goals of source analysis tools and source tools in general are the same as the binary analysis tools. Both things you want to be able to edit the code, either patching the binary or patching the source code. You want to be able to search, you want to be able to find vulnerabilities, you want to be able to know if my source has any vulnerabilities. And we're both building the same feature sets ultimately, and we're just getting to them from two different angles. So I think that's an interesting way to think about this going forward. At some point, we might not call this bar anymore. We'll have to add source somehow because they'll be the same thing. So I also just want to thank all of you for your inspirational work. Just seeing all this stuff, I'm like, oh man, I got to talk to that person. I got to talk to that person. I got to talk to that person. This has been like the best con for me. So yeah, thank you. Any questions?
All right, that's an amazing keynote. Any questions from the audience? All right, I'll start over here.
Hi. So when you were talking about SourceHammer, does that operate strictly from like a source compared to BNIL level, or does you need to like build the source at all and then lift it to BNIL?
It uses Tree-sitter, I believe, to be able to handle like partial source. Uh-huh. And then it does an AST to AST match using, really Yeah.
Gotcha. Cool. Thank you.
Yeah.
When you talk about, extraneous, sorry, I forgot the exact term you used, but essentially bringing, information from the outside to help the analysis. And you mentioned, using LLMs or machine learning for that kind of things is, a clear avenue for that. And I don't disagree with it, but I was wondering what's your take on the, the fuzziness of LLMs, for example. What if you bring information that's not exactly the information you want to bring, right? It looks like there are some challenges here that are, not necessarily obvious. It's not necessarily obvious how to solve them in order to, preserve the accuracy of information you're pulling from outside sources. Not that the analysis we have at the binary level are always accurate anyways, right? It's a lot of heuristics and so on. But how do you see this working out in that context?
Well, I mean, garbage in, garbage out, right? So it's super important that we pull in the right context. Yeah, you're right. It's a problem that we'll have to deal with to actually make better inferences. In some ways, we could use the LLM itself to be able to determine what the applicability is. There's also other ways that we can bring in information other than specs. You could potentially use images of PCBs to be able to say, okay, well, like I see it writing to these GPIO pins, and then I feed it in the picture, and it's like, oh yeah, and that's connected to this motor controller. And now you're feeding in the specification, and it's like, this isn't the specification for a motor controller. This is the specification. So I don't know. It's a little hand wavy, but yeah.
Other audience questions?
Thank you for the talk. I really appreciate it. Far as techniques on automated decompile, have you looked into or any future works on VM Protect code?
Say that again?
VM Protect.
VM Protect?
Yeah. Has any future works going towards?
I've not looked into VM Protect at all.
Obfuscation.
So.
This is obfuscation technique. Some of the bad actors
Yeah. I mean, I know.
Use it in the automated way. Of course, there's manual ways. I didn't know if it.
Yeah, I mean, I know of multiple people that have, in particular, written binary ninja architectures that are able to deal with virtualized protections, and so you just feed in the opcodes. Okay. Obviously, there's caveats to that because it's not always just that easy of getting the opcodes. So.
And just want to make sure the Sidekick is available for free for users.
No, that is a paid add-on to our existing product. Yeah.
We have time for a few more questions, if anyone.
Hi. So back when I was first learning reverse engineering, like decompilers were not readily accessible and available, and so like learning was very different than now when I'm teaching kind of new generations of reverse engineers, and they ask me like, I've got this decompiler, why do I need to really be intimate with the disassembly? And I'm the crotchety old guy being like, no, you have to know how this all works. In this world where we have like your vision is realized and we have these tools that incorporate all this extrinsic analysis and whatnot, what do you see are like the fundamental competencies, like things that reverse engineers will need to know to be effective at what they do for vulnerability research or whatever the task is?
Yeah, that's a very interesting question. And I think the answer is static analysis can be easily thwarted by obfuscation. I can tell you how to beat binary ninja in obfuscation using obfuscation. We were even talking about that last night at dinner. I think ultimately there's it kind of depends on what you're actually trying to do. Are you trying to do malware? Well, obfuscation's still a thing, and people are going to invent new obfuscation techniques, and then we're going to have to invent new static analysis and dynamic analysis techniques to get around. And so that's probably going to be around for a while, is just being able to deobfuscate things from that perspective. From a vulnerability research standpoint, like pretty much if you're doing binary analysis, then the next thing you're gonna do is exploitation, and like if you don't know the assembly, like sorry, the decompiler is not gonna help you to exploit anything. So I think there's still a lot of room for knowing assembly.
Thanks.
So thanks for the nice talk. I have a simple question.
Yeah.
And it's a question for everyone else. You don't have to give me a positive answer. So, do you have any plan for like educational discounts for the licenses?
It's a 75% discount on the licenses for education.
Okay, cool.
And plus, we also give grants to, like, if you're doing research to like Dr. June, his research is like on doing the disassembly and decompilation. Like, we're happy to talk with you about like license grants for that kind of research, because it benefits us like 100%. So
cool. Thank you.
Yeah.
Any other questions? One last question.
I had a little birdie told me. Are you looking to incorporate Sailor into Zendeco? Let's talk a little bit about that. We're
definitely familiar with the paper. Before we would look at that, we need to. I question how good their metrics are. So, like, they did an amazing job. Like, I love that paper, and like, it's exactly the kind of research we need to do. It's like one of the first ones to be like, oh no, here's a metric. We made it up, and we're measuring ourselves against the metric, and look, we proved it's perfect. It's just what we need. We also need other metrics, and we need someone else to say, like, ha, you made a metric, and here's where it's broken, because that's how science works, right? So, yeah, but there's definitely techniques in that I'm just like, oh no, we need to do that. So.
I can imagine there's probably lots of opportunities in presenting users with different options, right, in terms of how the output is formatted. I mean, certainly Binary Ninja has different levels of IR, but even at each of those levels, there's probably, from looking at Sailor, or I think there was a paper called Dream a few years back that was looking at, how humans would prefer decompilation to look.
Go-to lists, decompilation. And we actually looked at that paper before writing ours, and we said they've got some great techniques, but we think that go-tos are important. So we're like, you don't want to completely remove them, and the Sailor paper said the same thing. They're like, yeah, go-to, no, but you know what would be great? If we did have a version without go-tos, because your analysis is a lot easier. If you can have a normal control flow graph without any, there's never going to be a go-to, then you can run a different set of analyses that you could vastly simplify certain types of analyses by knowing you're not going to have this random edge.
Yeah, and I'm sure there's probably different, outputs that are good for, a human's mental model of how the program works versus, if you were to actually do bug hunting or re-instrumentation on the decompilation, right? And maximize different metrics that way.
If you want to run CodeQL or SemGrep or something like that, well, in that case, you really want it to be as close to the original source that, it was written for. And so that's kind of what the Saylor paper is trying to do.
Mm-hmm.
So, yeah.
All right, let's thank our speaker. All right, we're going to kick off our second session of the day called New Frontiers in Binary Analysis. We'll start with our first paper, libafl-QEMU, a library for fuzzing-oriented emulation, presented by Romain Malmain from Eurocom, with co-authors Andrea Fioraldi and Aurelion Francilion.
Thank you very much for the introduction. Then, as you just heard, I'm Romain Malmain. I come from Eurocom in France. I've been co-working on this paper with Andrea Fioraldi and Aurélien Francillon. And part of this work was also code hunting during an internship at Intel. And we have been working on libafl-QEMU, a library based on QEMU that we reuse into a state-of-the-art fuzzer, libafl, for fuzzing purposes. So very quickly, I will represent once again what fuzzing is, but I guess most of you are already aware of what fuzzing is actually. So fuzzing is the process of testing a program repeatedly by feeding it with some input. We check what the input does as some kind of feedback, and depending on this feedback, we mutate this input and try to find some objective, typically crashes. One very typical feedback for fuzzing is coverage-guided fuzzing, where we use we try to get what edges are hit during execution for one given input, and depending on these edges, we will try to check out if the given input has discovered new edges into the target program. We keep all of this information into some kind of bitmap, and then we mutate the input if the thing we discovered is new or not. We are actually performing coverage-guided fuzzing with libafl. Libafl is a framework built to create fuzzers. There are like a bunch of techniques that has been implemented into libafl in Rust, and it's actually very easy to choose like the kind of techniques you want to use for some specific target with a state-of-the-art implementation. Very fast, it's compiled, and use everything as a standard executable so that you have nearly no performance overhead. Thanks to compile time abstraction, it's possible to have like a very large code base with a lot of different techniques and just compile whatever is required to test your target program. The motivations behind libafl-QEMU are various. Existing solution has some limitations that we are trying to tackle. First, compile time instrumentation, that is the most used solution for this kind of problem. There are some limitations linked to this, as I just said. First, compilation is quite difficult to handle, especially because of the different toolchain you can find out there. Maybe people into embedded programming know what I'm talking about. The source code is obviously not always available for multiple reasons, because it's lost or because it's not given to the end user. And also, the instrumentation cannot be easily changed dynamically. It's possible, but much more tricky. Also, on the other hand, the static binary rewriting technique has also various limitations. Usually, you cannot just rewrite any binary statically, but only some subset of what's possible. I was thinking of the C++ exception handling process that is very tricky to get right with static binary rewriting. Self-modifying code, a very, very tricky thing to tackle also. It does not support full system, as far as I know. I am not aware of any static binary writer that supports full system targets. And it's usually tightly linked with one or two specific ISAs. There are some exceptions, of course. Like I was thinking of Revenge that is currently being developed, but usually it's not the case. And then here comes QEMU. I also think many of you are aware of what QEMU is, but I'm going to represent it very briefly. It's an emulator that is able to emulate a very vast amount of architectures, among them the x86, x86-64, ARM, but also more esoteric architectures. It supports many different platforms. like the PC, that is a very complex platform, but also more simple platforms that you can find in the ARM world. It's very actively maintained. You have thousands of developers there that are pushing into QEMU daily. It's mainly split into two modes of operation. User mode emulation, that is re-emulating Linux or BSD applications so that you are able to run binaries that has been compiled, let's say, for ARM, like Linux binaries, on an x86 processor. And then you need, at this point, some kind of system call handling so that you can translate the syscall accordingly. But the other way to execute things in QEMU is a system mode emulation that is able to re-emulate entire machines. Think of like a CPU processor with a PC platform. It's also able to emulate the MMU completely. As far as I know, it's very complete. And there are also a bunch of devices available. Obviously, not every device is implemented there, but at least the minimal devices required to run complex targets are already there. QEMU works this way. I'm going to be very high level there. Sorry about this. First, you have the target binary code. That is the application that you are trying to emulate. That is going through some kind of disassembly until you get through like an intermediate representation called TCG. And then this intermediate representation is once again translated into the host binary code so that you can just execute the code on your native architecture. Going through TCG has some advantages, and one of those is to be able to instrument it, to actually perform some kind of operation at a higher level so that you are able, let's say, to instrument read or write to memory, and all, I don't know, additions, if this is what you wish. Like it's very versatile. So we come up with libIFL QEMU. The existing solutions trying to use QEMU for fuzzing are some limitations. One of those that are very popular these days is AFL++ QEMU. The main problem of this implementation is the lack of flexibility of these solutions. And this has some huge drawbacks. One of those that is very common is to be hardly maintainable and updatable with the new updates of QEMU. Usually it requires like a huge amount of work to get these solutions actually merged with the QEMU updates. And the consequence is that these solutions are usually upstream with old version of QEMUs. One, I'm thinking especially of Pandas that is based on QEMU2 that is very, very old now. And also the solution, the CXM solution is not easy to actually merge with libIFL that is heavily being developed right now. So what we try to do is to turn QEMU, a standalone executable, into a statically linked library. Like the idea is to play a bit with how QEMU is being compiled so that we can get this intermediate objects and then link all of those into our libIFL executable and call QEMU functions. That way, it will be like kind of a very good solution performance-wise because you will have nearly no overhead doing this way because you are just calling QEMU functions directly without anything between you and QEMU. And above this, you are able to create safer abstractions to avoid the user manipulating unsafe C functions and safely handle QEMU in a more meaningful way through, let's say, Rust abstractions in our case. Here is a high-level idea of what we've been doing to get to this architecture. First, we tweak a bit the QEMU compilation process to make it compile into a shared object. That way, we can access the command line that is being executed to compile this shared object and extract all the intermediate objects that has been used to get this shared library. Then from this, we create this partially linked QEMU version so that we can finally link this into the libIFL object files and get the final binary. The main benefits that we have seen so far are listed there. I will also quite briefly go over there because they are quite numerous there. First, the most important point, in my opinion, is that we didn't need to modify too much the code of QEMU. We tried to make it as little as possible so that it's easy to maintain and to keep up with new QEMU versions and get the new features integrated and have a very lightweight performance overhead above QEMU. We are able to support multiple architectures. They are not like the whole bunch of architectures that QEMU is implementing. It's mainly because it requires some custom code to have an architecture implemented. Not that much, around 300 lines of code, but it's still some work that we didn't do yet. And the flexibility is also an important point, in my opinion, because we already have many different hooks implemented to be able to, let's say, catch every read or write to memory, do some operation when an instruction is executed. And also, this solution is linkable in other projects. And if you want to have QEMU as a library in your own project, it's actually possible to reuse our work to link it to your own project. And then you can use QEMU in a high level, with high-level abstractions without having any compromise on performance and usable features. Here is a list of the hooks we've been using so far. The most important ones are like the block and edge hooks, especially for fuzzing, to get this coverage feedback. Read and write also is very interesting. Also, the crash feedback that is really used to get the objective of the fuzzing campaign, and some things like thread and syscalls. These are not available in system mode because they are abstraction of the operating system, and thus we cannot easily access them. It's possible maybe with like VM introspection, this kind of stuff, but we are not doing this right now. With ABFX QEMU user mode, we've also been working hard to have some features related to fuzzing working above this, to have some kind of useful tools that we can use to find more bugs, especially QASAN that is able to detect memory corruptions at runtime, snapshotting to avoid restoring the whole process each time a fuzzing run is over, and make sure to restore the target very quickly. And advanced range filtering. This is very useful to have limited feedback, to get feedback from some part of the code. This is sometimes necessary to have good stability during the fuzzing run. And then we have the system mode part that is also implementing its own fast snapshotting mechanism that is independent from the first one because they don't have the same underlying construction. In addition to the advanced range filtering, we also have paging filtering that is very useful. It's especially the case when you are like running a full kernel in QEMU, and that then maybe you want to just have feedback from one process. That is usually the case, or maybe two processes at most, and about all the noise around. This is possible with this feature. And we also make heavy use of what we call the custom QEMU exit instructions. They are like backdoors into the target VM to go out of the QEMU VM and communicate with the fuzzing harness. Here is how it works, like this QEMU exit instruction feature roughly. You first execute the custom instruction into the QEMU target, disposes the VM and goes to the harness with some kind of command that you can communicate through the registers of the VM, for example. Then you can execute any command that you may have to execute, like maybe you want to ask to snapshot your VM or feed your VM with some inputs. And then you can resume execution. Apart from this, we also have this breakpoint way to communicate with the harness. The process is a kind of reversed because this time the harness will be the one to set a breakpoint into the VM. And once this breakpoint is triggered, the VM will stop and then the harness will be able to perform some action. This is, depending on the situation, one or another can be useful. It's really extremely dependent on the target. But so far, this is the main things we've been using to build our own harnesses so far. To showcase how this is working, we built two experiments. One using the QEMU user mode with RM64 architecture. We fed the Samsung Android parsing library to reproduce some bug findings that we've seen in Google Zero blog post, Project Zero, sorry. And then we also fed in system mode the Windows 10 NTFS kernel module to also show that we are able to handle very complex targets like Windows 10. This kernel module, as the title is quite explicit there, it's parsing NTFL file systems to be able to plug USB devices and be able to show the file there. It's run on an x86-64 architecture, and we compare this with KFL. User mode experiment first. We just run the hardness with both libafl QEMU and IFL++ QEMU and compare the performances. We're able to get a 3 times faster execution and 1.3 larger block coverage into our implementation compared to AFL++ QEMU. And this is with just the persistent loop, there is no special feature running there, it's just like a fuzzing loop. And then when we enable QASAN and snapshotting, we get 2 times faster and similar block coverage. But we are able to find two bugs where the other IFL++ QEMU cannot find anything. For the system mode experiment, we run the same hardness for libafl QEMU and KFL. The goal there is to show reproducibility for complex targets. Obviously, we cannot compete with virtualization. That is obviously much faster than emulation. But we can show at least that we are able to execute the same kind of targets. And also, we try to compare our own snapshotting system with the one implemented by default in QEMU. And we're able to have great speed up, especially at safe time. And but even though the restore time is still much faster. The limitations are shown over there. We have no retrocompatibility with the older version of QEMU, which means that you can only run anything that is running in the last version of QEMU. If you have an awesome project developed for QEMU 4, I think it will be quite hard to merge it with our implementation. We can also run whatever QEMU runs, which is both a good thing and a bad thing. If you want to target something that is not implemented in QEMU itself, it won't be possible. And for now, we have no virtualization support at all, which means that we are not able to get state-of-the-art performances. For future work, we would like to support this virtualization feature, actually, have some kind of KFL-like system implemented with our own harnessing system to have some kind of unification of harnessing that we believe is very important. And we would like to extend libafl QEMU even further with new feature and continue to update it with mainline QEMU, QES, exactly. To conclude, we try to build a future-proof QEMU implementation and integrate it with libafl. We try to support as many architectures as possible and make it easy to add new architectures. We support both user mode and system mode. That is not always the case with similar projects. And we experiment this implementation with Windows kernel fuzzing and Android library fuzzing. We already have many features and hooks implemented. But of course, I truly believe that it can be extended even further with awesome features that I hope people will be able to bring to the repository. And you can already find these implementations on GitHub. Thank you very much for your attention.
All right, any questions? Okay.
Thanks for the talk, Manuel Egele, Boston University. So I have a quick question that you could talk a little bit more maybe about your state resetting, especially for the devices. You mentioned that it's faster than QEMU's. What we realized is that QEMU's is not only slow, it's also incomplete. So state will accumulate over time if you use that for fuzzing campaigns. So in our past work, we had hence to fork instead. Yeah. So if you could tell us a little bit what you did to speed this up, this would be great.
Yeah. Very, very good question, actually, because we have, as I showed there, we split the snapshotting system into 3 main parts. The RAM snapshotting, CPU, the block device snapshotting, hard memory, and then the device snapshotting. Device snapshotting is very difficult to tackle with because you have nested structures, pointer, restore. It's a very hard process. For now, we are keeping the QEMU system for device snapshotting. It's on purpose, let's say, because we didn't notice any speed up with doing some fancy tricks like trying to get which part of the device memory can be saved and restored. Like I saw this implementation in KFL. Like they actually do this. Like they like collect all the part of the memory that is used into the devices to restore them when they want to restore the snapshot. But there is no real speed up, I think, there, or at least I didn't notice it. And it's actually very device dependent, and we wanted to keep it device independent as much as possible. Thank you.
Other questions?
Florian Hofhammer, EPFL, really cool talk. I like that this is basically trying to have a QEMU integration that is a bit more bleeding edge, because yeah, I've seen that a bunch of times in older research artifacts where super old QEMU versions are used for whatever you do. You mentioned on slide 12, I think, that like you had to change approximately 2,000 lines of code in QEMU. Do you have a breakdown on how much of that is actually code for QEMU itself and how much of that is the build system that you needed to modify to link it into a static library?
Yeah, thank you for the question. About the build system first, we did like very little modification actually to make it work. Surprisingly, we'd expect like to have crazy build system modifications to have this shared library target, but they like a few years ago they switched to Mason, and it was actually quite easy to get the shared library system. It's about, I would say, 50 lines of code of modification in the build system itself, which is surprisingly low. I agree with you. And the rest of the line of code is mainly into like the QEMU core system to have the hooks implemented, be able to execute the backdoor to detect all these things. We also have a separate folder into the QEMU project where we have our own code that I didn't count into this line of code, because I believe there will not be any problem when we want to merge QEMU, since it will be ignored by the merging process. But yeah, basically this is it.
Sort of just a follow on to that question. So have you actually forward ported your patches to different versions of QEMU from when you started? And if so, how long did it take you to sort of forward port your patches?
You mean how much time we need to merge new QEMU versions?
Yeah,
very good question. We have been trying this out in real life, obviously. Like we tried to merge new QEMU version over time. Each time a new stable version is released. I think so far we've been like merging 3 or 4 like new release versions, and it seems to work. At least, I mean, I cannot predict how it's gonna be in the future, especially when you will have yet another rework of the JIT system. But it's impossible to predict. I guess at this point we will have a lot of work. But for the more minor modifications, it's very very straightforward. Like we just git merge, resolve a few things that are conflicting that happens, but I would say in terms of time, it's maybe 30 minutes of my time.
Oh,
I guess it's worth my time at this point.
Cool.
Thank you.
And presumably Mac OS is also doable, right? Assuming you have an image for the kernel that you can load like you did for Windows.
You mean for Mac OS fuzzying, for example?
Yeah.
I'm trying to think if it would be a problem because I didn't try it myself. I guess as long as it runs this QEMU, I think it's going to work out of the box. Of course, I may be wrong. I cannot predict if you have like a very edge case that will break everything. But we try to not like to have some interaction with QEMU itself. We just try to let QEMU run as if it was a normal QEMU and just have our code running basically when we trigger things that are fuzzing related.
All right, wonderful. Let's thank our speaker.
Thank you very much.
All right, for our second paper, titled Efficient Normalized Reduction and Generation of Equivalent Multivariate Binary Polynomials, we have Arnau Gemez-Montolio, sorry for mispronouncing, with co-authors Enric Florit, Martin Brain, and Jacob M. Howe.
Okay, so this paper is mostly a math paper for the most part, but very, very motivated by practical applications on binary analysis and binary transformations. So that's why we decided to submit it here. Even if the core of the paper is just a bunch of math, the motivation and the applications are essentially practical in a sense. I'm Arnau, main author of the paper. I do my PhD at City University of London. I work at Activision doing security things. And as I was saying, the motivation is basically being able to use polynomial transformations and invertible polynomials as obfuscation primitives. And let's see what does look like. For example, we have data encodings transformations, which allow us to prevent data values used on some arbitrary computation from being revealed during program execution. So we have some constants that we want them to be hidden from program execution. We can use that. We can use, for example, this sample code, very, very simple CLI code. And we would like to hide the key 1 and key 2 to never appear right away in the code. So we leverage a bunch of polynomials, in this case just of degree 1, P and Q. They are inverse polynomials, and the idea is we can essentially encode the constants P, A and B with the polynomial P, and then at a point where we need to use them, kind of decode it on the fly. And the resulting code in source code looks like that. At this point, key 1 and key 2 would never appear in clearing the code. Another example is certain identities, which is as simple as wrapping an expression that we want to complicate with a couple of functions, in this case polynomial functions with one higher degree that are inverse. So their effect will vanish essentially. Again, very simple example. Have a couple of polynomials. Again, they are invertible. They're inverse one of each other. And we just replace the result by chaining them together. Okay? This is the result in this case. And again, we have kind of obfuscated the addition that was happening there. Another one example, just again to motivate more, why do we care about this from a math point of view, is opaque constants. And this time, what we want to do is we want to use some constant, but instead of having any kind of constants or even encode it, we want to replace the use of the constants themselves by some computational process that will compute them at runtime. Okay? And again, we can use polynomials as primitives to build that. Imagine that we have some 8-bit constant that is used as a parameter for some function that does whatever. We use some expression that has to be equivalent to 0 and a couple of permutation polynomial, more primitives. And we just build that transformation. And if you take a look, the semantics of the E expression are essentially 0, as we see. And then it boils down from a semantic point of view to P of Q of K, which is, again, just the constant K, just computed at runtime. So instead of using the constant, we would define auxiliary constants, X and Y, and then instead of passing our 123 constant, we use a runtime operation that will compute them at evaluation time in runtime. So that's kind of the motivation behind that, why I started doing research in this kind of things from my point of view. And the goal is essentially, from an obfuscation point of view, we want to generate equivalent polynomials. We want to be able to say, okay, I have some polynomials that do something from a function point of view. I want to generate equivalent ones. In order to increase diversity, so I can distribute different versions of the same code, the same expressions, the same routines that have the same semantics, but they are not easily matchable. And also to introduce arbitrary algebraic complexity. And this is essentially to thwart analysis techniques, both from SMT solving capabilities. They struggle a lot when you introduce high degree and a lot of complexity from interleaving logical and arithmetic expressions, and also compiler and decompiler optimizations. From an analysis point of view, we would like to, within the framework of dealing with equivalence, reduce binary polynomial to a unique normalized equivalent representative that has some nice properties, and essentially what I'm looking for is lowest degree, to have the lowest degree guaranteed. So this is a representative of my function as a polynomial that is guaranteed to have the lowest degree. So any other polynomial that is equivalent will be as little as the same degree that we have there over this one. And this is very useful for a lot of the obfuscation efforts I find in the wild, and also for general algebraic manipulation, both from the point of view of a computer algebra system and also SMT solving. we need to talk a little bit about null polynomials, modulo powers of 2. And again, modulo powers of 2 is just working with word size W. Okay, when we say modulo power of 2, we just mean working on RW bit values. And the basic idea that we realize is, okay, imagine that you have an arbitrary polynomial that is whatever, and then we have another one, which we call Z, that is semantically the constant function 0. So essentially, if we add those together, we add some polynomial with another polynomial that is 0 semantically, we get another polynomial which has to be equivalent to the first one. This is an example. First one is just a random polynomial. On 8 bits, you see modulo of 2 to the power of 8. We get Z, which is a null polynomial, a 0 function polynomial. This is a polynomial that will evaluate to 0 for any input. And if we just add them together, we get another polynomial that will be equivalent to the first one by definition, because we are just adding a semantic 0. So in other words, if we have 2 equivalent binary polynomials, then its difference has to be another polynomial that is semantically equivalent to 0. And it might be non-trivial. That's kind of the idea. So that's what I just said. We have 2 equivalent polynomials. I subtract one from each other. And what I get has to be equivalent to 0 as a polynomial function. And we call those Z as null polynomials in the bit size that we're working, in the modulo that we're working. Now, just a little bit of notation. Just you can completely don't care about the notation in here and just follow the examples, but I want to introduce just a tiny bit of math that I need to focus on the examples later on. The idea is, okay, we have said we need null polynomials, and if I can, kind of the idea is, if I generate all the possible null polynomials, then I can just generate every possible equivalent polynomial to one given. So I get one polynomial, I generate an arbitrary null polynomial, I just add them together, I get a new one, which is equivalent. So now I'm interested in generating those null polynomials. Just some concepts. I define these polynomials that have some nice properties. And the nice property, I'm just going to focus on this example on the left, is that there's a polynomial in which it's a product of decreasing terms. So you see it's x minus 1 times a constant. And the idea here is that I have a product of decreasing terms which will have some parity, some number of 2 factors in there. And I just need to compensate that with a constant that will make sure that the polynomial will be 0. So for example, this very simple example, x times x minus 1, for any x, I have guaranteed that either x or x minus 1 will be even. So I have a 2 in there. So what is the constant that I need to compensate so I make sure that I will have a 0 in here? It's 2 to the power 7 in 8 bits. So that will mean that for any x, I will have 2 to the 7 times something where an even number is in there. So I is guaranteed to be a 0. And we can build those polynomials in general. You have an example. It's just exactly the same, but with G4 in this case. That's kind of the idea. As I said, for any index, these polynomials constructed in this way will be equivalent to 0 by definition, like by construction. I'm constructing them in a way that I just make a pile of decreasing, a product of decreasing terms, and then compensate it with the constant that I need to make sure that what I end up with is a 0. So some facts that we realized in the paper is, for example, this set of polynomials generates the whole set of null polynomials and it's minimal. That is great because we see that that's a finite set. We see that we need to define this DW, which again is nothing super special, but just for you to know the notation. This is essentially at which point the number of 2's in the factorial of that position go beyond the bit size. So in 8 bits, for example, that would be 10. For example, if you make the 2-adic valuation, which is just counting 2's of the factorial of 8, you see that's 2-adic valuation of whatever with a 2 to the 7. That's a 7. That's the number of 2's in the factorization of that, which is not yet the bit size. But in 10 factorial, we are already there. So this DW, this limit for that, is what defines the last element of the set of generators. And this number will be important for a number of things later on. When I say generate, it means that any null polynomial can be obtained by combining those together with other polynomials and constants. And minimal means that if I remove any of the polynomials in that set, I would not get the whole thing, the whole set of null polynomials. Let's talk about the factorial basis, and it's just Okay, how do we go about actually applying that to polynomials? We are going to think of polynomials as elements of a vector space, which is a fancy way of saying I'm just having a constant times one element, which will be the one for the coefficient without any variable, another constant times x, another constant times x squared, and I'm going to make a change of the basis. I'm going to plug that into a basis which is 1x, x, this parentheses of 2, parentheses of 3, which are defined as this factorial product, this decreasing factorial product. And that has a number of nice properties that we have hinted before about distribution of parity, a guaranteed distribution of parity within the expressions. So for instance, the G2 that we saw before, in canonical basis will be 128 for 0, which is 128x plus 128x squared. In canonical, in factorial basis, is just a 128. We have for the G4, and we could go on. An important thing to realize is that by construction, those G sub j that we saw are essentially in factorial basis a single coefficient, this coefficient, the coefficient, the leading coefficient for the G's as we define them. And this coefficient collapses to 1 when we are up to this dw by definition, because we will have the max of 0 and the bit size minus the two-adic valuation of the factorial of the position. By definition of the G's, will collapse at 1, will collapse that to the power of 0. So that gives us a kind of the idea about adding an arbitrary null polynomial is essentially adding arbitrary multiples of these coefficients to each one of the coefficients of our polynomial in this factorial basis. So we'll go right away into algorithms and examples to actually visualize what I'm talking about. How do we generate equivalent binary polynomials? Well, let's take a binary polynomial, represent the coefficients in the factorial basis, and then add an arbitrary multiple to each coefficient, depending on the position of the coefficient, and then represent the new polynomial in a canonical basis if that is needed. Okay? And the arbitrary multiple of the appropriate coefficient that is defined by the G definition that we saw before. So for example, in 8 bits, I do have my examples in 8 bits because it's just smaller and fits better, but it works on 8 bit size. We got this polynomial, which corresponds to 0, 97, 248 in canonical basis. We represent that in factorial basis, which will be 89, 248. And then we are going to add arbitrary multiples of the Cj to the jth coefficient in this form. So for example, we add C2 on the 248, then 3 C4, 2 C7, and then a bunch of 0 and 27 C16. That is exactly what is happening here. The C4 is 128, the C3 is 128 away, the C4 is 32, and the C7 is 16, and the C16 is 1. So we just make this addition, and we end up with this new set of coefficients in factorial basis, and then we convert that back to canonical basis. So we can't just make the base of changes or just evaluate the new polynomial. We get this new polynomial, which is essentially written at that way, which is equivalent to the initial one that we got. Okay? And we can do kind of the same idea for the reduction. So take any binary polynomial, and we represent the coefficient in the factorial base, and now the concept or the intuition behind let's remove all the verbosity of zeros that we don't need is represented by let's get h coefficient on the position of j and reduce it modulo the coefficient that is given by the basis of zeros of j elements of the zero, the set of null polynomial generators that we had. And now, if we need, we just represent it back in canonical basis. For example, in 8 bits again, we have this polynomial. We represent the canonical basis. It's just direct translation. We plug that into factorial basis, which gets us this polynomial. Now we reduce each jth coefficient modulo the Cj. Again, I have put you for clarification the vector of Cj's that we are reducing each coefficient. So we are going to reduce element-wise 0 modulo 256, 103 modulo 126, etc., and then we arrived to the set of reduced coefficient in factorial basis, and if we need it, we just convert it back to canonical basis, and we get a reduced polynomial, which has guaranteed lowest degree and some other nice properties in this factorial form. So we have that, for example. Some interesting facts. Each coefficient manipulation in this factorial basis and why we want this factorial basis, one of the reasons is independent. So all these manipulations and coefficient addition, multiplication, and reduction on a modulo is independent of the other coefficients. That means that you can just parallelize that. You can just run all at the same time. There are no interdependencies once we made this change to the factorial basis. Also, the degree of the reduced form of the polynomial in this factorial basis is preserved in the canonical basis. So if I have a reduced polynomial in factorial basis of degree 7, the degree in canonical basis will be preserved. So it means that it makes sense to talk about reduced polynomials in a general sense within this framework. Another fun thing is that if our bit size is a power of 2, which is what we all use, then that limit, the dw, is w plus 2. And there is a fancy way of saying that for any polynomial, any binary polynomial that we have on a given bit size, we will have an equivalent 1 degree at most w plus 1 because, well, kind of in this definition, the coefficients of the j elements of the set of generators will collapse to 1 once we are past that point. So we could just, okay, for the coefficients of higher degree, we just subtract a multiple of the appropriate element of the set of generator of the j. So we can get rid of all of them until the dw. So this implies, again, from a reduction standpoint, that we don't really need to compute coefficients starting from w plus 2 on a factorial form. We can just forget about them on the translation process from canonical to factorial and save a lot of things. So we have a polynomial in 8 bits of a degree 100. When we make the change to the factorial base, we can get rid of anything that is beyond 10. We don't care about it. It will collapse to 0. The multivariate, just very quick, I just want to mention that all these results and algorithms can be generalized to the multivariate case, and we did that in the paper. It's just the notation gets a bit tricky, I gotta admit. We made our best to make it as painless as possible. But the idea is we want natural generalizations of null polynomials on the factorial basis, and then everything kind of falls automatically. For example, we have this generalization of these elements generators. So in this case, we have to adjust for the parity that we'll get from one variable and also from the other one. It's kind of the same idea construction. Then when going from canonical basis to factorial basis, we fix an order on the polynomials, and then we can also think about them as elements of a vector space and transform kind of a natural way between this set of decreasing products. Just an example, we get this fancy polynomial in 8 bits. We represent in factorial basis. We reduce with each of the associated coefficients in the factorial basis. We get the reduced form in the factorial basis. We plug that into canonical basis again, and we get x squared, y squared. Those two polynomials are equivalent on 8 bits. Just as a conclusion, we made a thorough mathematical study of binary polynomials. I didn't want to show a lot in here because it gets pretty dense. But for the most part, we proved a bunch of stuff that we needed to make the case that this is actually true and this works and why it works. So we provided a characterization of equivalent binary polynomials, and when they are equivalent, also explicit algorithms to generate arbitrary equivalent polynomials and make reductions of binary polynomials to a normalized and lowest degree form to be guaranteed. And that's all for me. You can reach me out through email or just on my website. There are a bunch of links to places where you can find me. Thank you.
All right. Questions from the audience? So is this a really common obfuscation technique that you see in the wild? I've been kind of wondering.
Yes, essentially, I'm not sure how much can I talk about that, but we see a lot of obfuscation, and the one that is good obfuscation introduces polynomial transformations, because that's essentially killing either the compiler, it's essentially killing Z3 as anti-solver when it has to reason about is this equal to something else. So high degree, even if semantically is equivalent, you introduce high degree, which is polynomial transformation that are nonlinear. It kills a bunch of things kind of for free. And also I'm interested in the part of diversity. It's like not only killing tooling from the point of view of protecting binaries, but also being able to make, essentially I want to distribute a bunch of code to a multiple of clients, and I want them to have some, like the same semantics on some transformations, but I don't want them to be able to match what are they talking, that it's the same thing. So I'm using that as also as primitives for that.
Super cool, super cool. I'm guessing certain video game companies are employing such obfuscation techniques. Any questions?
Is this, isn't this the kind of obfuscation that Goomba, the IDA plugin, is?
Yeah, that's a very good question. Goomba is a NIDA plugin that comes like right away since the last version, I think last couple of versions, which targets mixed Boolean arithmetic obfuscation, which is an obfuscation that essentially transformations that combine Boolean operators and arithmetic transformation, which are another way of killing SMT solvers and other stuff in general. We use, or when I say we, in general, in the literature, polynomial transformation have been used in combination with MBAs. Actually, there's one of the examples in here about the insertion of like the opaque constants. Yeah, just give me a second. Yes, this E opaque, like this is a non-trivial equal to 0 MBA. You see this E, X, or Y, that is an MBA that I'm using as also as a primitive. Goomba targets this kind of obfuscation in general. For my experiments, Goomba works nice when let's say the binary is very well structured. So you just put your MBA very clearly. And even minor modifications that maybe just the compiler does on some optimization pass, that kills Goomba in many places. That being said, this is not exactly the same. So this is like the research here provides obfuscation primitives and analysis primitives from a point of view of building polynomial transformations that can be combined with MBAs. And in that sense, if Goomba at some point targets or gets refined to address MBAs with high algebraic degree in general, that could be a thing that they could use from the analysis of simplification point of view, or they could target. But right now, Goomba is just attacking MBAs on its own, not polynomial transformation in general.
Thank you. Other questions? All right, super interesting stuff. Let's thank our speaker.
Thank you.
Okay, for our third paper, we have CBAT, a comparative binary analysis tool. Authors Chloe Fortuna, Chris Casingino, Sam Lasser, JT Pask, Cody Rue, and Philip Zucker.
Great. Is that visible? All right. Hi, everyone. I'm Sam Lasser, and I'm here to present CBAT, a comparative binary analysis tool. This is a Draper project, and this is joint work that I did with my colleagues Chloe, Chris, JT, Cody, and Phil. All right, so there are several reasons why you might want to compare the semantics of two binary programs. For example, maybe you've patched a binary and you want to confirm that the patch had its intended effect. Maybe you've instrumented a binary and you'd like some assurance that the instrumentation code doesn't interfere with the application code. Or maybe you've written a new compiler optimization and you want to check that the optimized version of a program has the same input-output behavior as the original version. In each of these cases, you can benefit from using a comparative binary analysis. In other words, an analysis that statically checks a relative correctness property over a pair of binary programs. Now, ideally, when one of these checks fails, you would like the analysis to help you understand why it failed. And it would also be nice to perform the analysis in a platform-independent way so that you can reuse it on binaries that target different architectures. So in this talk, I'll present CBAT, a binary analysis toolkit that aims to satisfy these criteria. The core of CBAT is a differential program analysis tool that's built on top of an open source binary analysis toolkit. The inputs to the tool are a pair of binary functions along with a relative correctness specification. The tool first uses the binary analysis platform, or BAP, toolkit to lift the binaries to a platform-agnostic intermediate representation. The tool then performs a weakest precondition analysis over the lifted functions along with the correctness spec to compute a logical formula that is true if and only if the specification holds. And then finally, the tool dispatches that formula to an SMT solver that checks whether the formula is valid. CBAT includes a number of supporting features as well, including a library of built-in correctness specifications, an interactive debugger for understanding why property violations occurred, and the ability to integrate with multiple SMT solvers. CBAT is implemented in OCaml, and the open source development is available online at this URL. All right, so I'm going to introduce CBAT by way of an example involving this slightly simplified program that controls a vehicle. The function process message that's shown here takes two parameters, a message type T, which is the enumerated type shown at the top of the slide, along with a message M, which is some struct. The function dispatches on the message type in order to invoke the appropriate handler on the message. So for example, a nav message type adjusts the vehicle's heading, a log logs the vehicle's current status, and deploys a research payload. Now, you'll notice that the developer of this program has decided that every heading adjustment should be logged, and for this reason, they have omitted a break keyword from the nav case. And as a result, every navigation event is followed by a logging event. Make sense? All right, now suppose that later on, the maintainers of this code decide to remove the logging feature. I'm showing the modified program in source form for readability, but we'll assume that the patch is applied to an x86 binary. So now the program has a bug, namely that the nav case falls through to the deploy case, and every navigation event unintentionally triggers the, or causes the research payload to be deployed. All right, well, we can use CBAT to check whether this patch had any unintended consequences. Now, because the patch is removing functionality, a reasonable property that we might check is that every run of the modified program calls a subset of the functions in the corresponding run of the original program. And by corresponding, I mean starting from the same machine state. So we can perform this check as I've shown on this screen by invoking the WP tool, which is implemented as a plugin to BAP. The arguments to WP, which is the differential program analysis tool, are as follows. So origprog and modprog are the original and modified binaries, respectively. The func flag specifies that we should compare the versions of process message in the respective binaries. And then finally, this compare func calls argument is a built-in relative correctness specification. And it says that essentially what I said before, which is that the modified function should call a subset of the functions that the original function calls in every possible initial state. Well, for this example, CBET is able to detect that the pair of binaries violate the specification. And in such a case, it produces a counter model, which is an initial machine state such that when the two functions begin executing from that state, they behave in a way that violates the specification. So you can see in the excerpt of the counter model that I've shown in this terminal that the register RDI is mapped to the value hex 2A, or 42. Now, RDI holds the first argument to a called function according to the x86 calling conventions. And you might remember from the earlier slide that 42 is the integer representation of a nav value. So the translation of this counter model in English is that when the first argument to process message is a nav, our relative correctness spec is violated. All right, now in some cases, it might not be immediately obvious why a WP-produced counter model leads to a property violation. So CBAT provides several facilities for helping users understand and explore counter models. So one way, what I call the static way, involves producing a control flow graph, or CFG, in which the execution path that's induced by the counter model is highlighted. So in some cases, by the way, you're not meant to read the individual intermediate representation statements on this slide. This is just to demonstrate what one kind of output that CBAT can produce. But in some cases, it can be helpful to look at two of these CFGs side by side and compare the execution paths that they take. Now, for some other counter models, a static view might be insufficient for understanding why the counter model leads to a spec violation. So for these cases, CBAT also comes with an interactive debugger called BillDB. And it's possible to invoke BillDB starting from a counter model that was earlier produced by the tool. So in this case, in this example, we've already produced the counter model and stored it in a file called init.yml. And when we invoke BillDB starting from this saved counter model, we can see that in the initialized state, register RDI is mapped to hex 42. And from this starting point, the user can step forward and backward through the function's execution, set breakpoints, etc. All right, so we ran a number of experiments to evaluate CBAT's performance. And in each experiment, we applied a transformation to each function in a large binary. And then we ran the WP tool sort of pairwise on every pair of functions, every pair of corresponding functions from the original and modified binaries, with the correctness property that the two functions should produce the same final values in Kali saved registers. So for each of these checks or runs of the WP tool, there are 4 possible outcomes. The tool can return SAT, meaning that it detected no property violation. It can return unsat plus a counter model. It can return an unknown value, which is actually a value that the underlying SMT solver can produce. For example, in cases where some of the theories involved are undecidable. Or finally, the check and timeout, and we used a 1,000 second per function time limit. So for our three benchmarks, our 3 data sets, the first involved running an instrumentation pass that supports integration with the AFL fuzzer. And we applied this transformation to a base 64 binary. And then we have two other binary transformations. One is based on a binary lifting and recompilation framework. The other is based on a tool called Embrittle that shuffles program blocks and renames elements. And we applied both of those latter two transformations to tar binary. The table shown here shows for each benchmark the total number of functions or problem instances in the benchmark. And then out of those, the number of functions or instances that were verified, the number of counter models produced, and the number of unknown and timeout results. So further work is required to determine whether the counter models produced in these preliminary experiments are actual property violations or false positives. But I'll just note here that CBAT has several sources of soundness or incompleteness in its analysis. So one example is loop unrolling. CBAT simply unrolls program loops up to a user-specified bound. So if there's a property violation that only occurs, after a number of loop iterations greater than that unrolling factor, then the violation won't be detected. Now, just as sort of an interesting tidbit, we found that, not surprisingly, the time required to compute a weakest precondition is proportional to the size of the function being analyzed. However, SMT solving time is not proportional to function size. And because SMT solving time dominates the total runtime of the tool, the total verification time for a given problem we found was not closely correlated with the size of the function under analysis. And this plot on the right shows the apparent absence of a strong relationship between those two variables. All right, so there's more material covered in the paper than what I've discussed here today. So I'll just give a quick sampling of other topics covered. CBAT performs differential program analysis via this program composition technique, where for two versions of a program, we take the second one, alpha rename the variables so that they don't interfere with the variables in the first program. Then we concatenate the two programs together and perform a single program analysis over the fused program or the product program. And this idea, I should say, is not novel to CBAT, but it's a clever idea, and I think we have a nice implementation of it. So earlier, I gave an example of a built-in relative correctness specification, but CBAT also supports user-defined correctness specifications. So you can invoke the WP tool with precondition and postcondition flags that come with logical formulas expressed in SMT-lib format. CBAT performs an intra-procedural analysis, so it doesn't trace control flow through function calls to keep the analysis tractable. However, we do support function summaries that enable users to model the behavior of function calls within the function being analyzed. And CBAT provides a library of predefined function summaries, as well as support for letting users define their own custom summaries. And then finally, as I mentioned before, CBAT has the ability to integrate with multiple SMT solvers. And we actually found in our experiments that SMT solvers have different performance profiles. And there are some instances on which, for For example, the Bool-Lecter SMT solver was much more performant than Z3, which is our default solver. All right, that's my talk. The URLs for the CBAT GitHub repository and a tutorial for CBAT are on this slide. And if you would like to discuss this work further, feel free to contact me by email. Thank you.
All right. Audience questions? Okay, so I saw, I'll let you ask first.
Thanks for the nice talk.
Yeah.
So we're kind of exploring similar questions, but we're just looking at the specifications. So what kind of specifications are built into CBAT? Does the code repo contains that?
Well, I missed the last part of the question.
I mean what's built-in specifications you have for now?
Oh, right. Yeah, so I showed an example of the compare func call specification. We have another, let's see, another example is like a trip asserts specification, that basically, that can be used to check whether asserts in your program are reachable or not. Yeah, those are the two that come to mind, but I guess, we also, there's a built-in specification for checking whether whether the return values that the two different functions produce are equal or not. So in the case of x86, the values, the final value stored in RIX. Yeah, I can't remember. I can't remember how many total built-in specs we have, but I think it's on the order of 10 or 20.
Other questions? Yep.
Yeah, thanks for the talk. Given that you have this differential programming analysis tool, did you consider checking for information leakage? Because you could basically just use the same program as the original and modified one, but just modify the secret state.
Yeah, it's an interesting idea. It's not something we've explored, but it does seem like a nice sort of off-label use for the tool.
I think also binary minimization. I know binary analysis tool developers, when they get test cases of, hey, this binary that we found in the wild causes weird issues, right, in terms of semantic divergence or whatever, in the decompilation or something, like having a way to pinpoint exactly the instructions that lead to that bug, I think could be interesting. And I don't know of any good binary level techniques for doing minimization. I think it's still kind of an open problem.
Yeah, I don't know about doing it in an automated way, but the CBAT was originally developed in the context of a program on binary debloating.
Interesting. Okay.
So I think more with the goal of reducing attack surface.
Interesting.
But I guess that would also be a benefit of debloating.
Very cool.
Yeah.
And then in the table where you showed that some of the queries you made were not solvable in the timeout, was it kind of clear cut that those that were unsolvable were significantly, or yes, those that were solvable were significantly faster than your timeout.
Yes. Yeah.
Okay.
Yeah. So I think we found that most instances terminated, in much less time than the maximum, or they didn't terminate at all. Or we found that even increasing the upper bound on time
didn't lead to more.
Didn't have an effect.
Okay.
Yeah.
Cool. All right. Any other questions? Okay. Thank you so much. Let's thank our speaker.
Yeah, thank you.
All right, and our fourth and final talk in the session will be on GTrans, graph transformer-based obfuscation resilient binary code similarity detection by Yun Zhang, Yuling Liu, Ge Cheng, and Bo Wu. I should clarify, they are on Zoom, sorry. Say again.
sorry. Yoon, Ge, can you start? Yeah, start speaking a little bit so they can adjust the audio.
Okay, everyone. All right. I'm very pleased to attend this conference and share Tim's idea. I'm the third author of this paper. I apologize that the first author cannot attend due to health reasons. So I'm here to replace her online. The main idea of our paper is to use graph transformer to address the singularity issue of the obfuscated binary code. As we know, obfuscation is an effective code protection mechanism that works by altering the data flow and the control flow within the binary code. Obfuscation can increase the difficulty of analyzing and understanding a program without changing its origin functionality. Effective protecting malicious use from reverse engine and cracking. Control flow flattening is a type of control flow obfuscation. It achieves obfuscation by transforms the program's control into a single flattened structure. On the left is the original control flow graph, and on the right is the result after obfuscation. Control flow flattening indeed add many basic blocks. In the diagram, the green node represents the orange basic blocks, while the blue nodes are basic block added to preserve the semantic control flow of the orange program. These blocks are used to simulate the logic flow of the orange code, but their sequence and structures are rearranged, making the entire program control flow difficult to understand. However, obfuscation doesn't destroy the immutable logic structures in the CFG, such as the dominance relationship. This is the key to use to transformer to address the obfuscation issue. GNNs aggregate by considering local structure information of the graph through the neighbor nodes, whereas transformer can traverse long distance across the graph to capture the global structure information without being limited by need for information to pass through multiple layers to reach the distance nodes. As in the case with the graph nature network, moreover, compared to the layer by layer propagation of the graph nature network, transformer allow for each node to independently compute its attention way, thus facilitating either pair program. In transformer, the structure information of the graph need to be encoded in a way that reflects the topological relationships distance between nodes. This enables us to address the challenging obfuscation by addressing structure information that relative invariance and changing detail phases of the obfuscation, such as the domination relationship. To process binary factions, we first need to pre-progress them to obtain their control flow graph and the dominance tree. At the same time, we generate embedding for basic blocks, which served as the initial feature victory for the nodes. Subsequently, within the CMIS network structures, we use graph transformer to generate embedding for the factions with the consistent similarity serves as the major similarity between the two functions. In the pre-progress stage, firstly, disassembly tools such as IDA Pro are used to obtain the control flow graphs of the binary function. There are corresponding assemble instructions. Then, based on the control flow graph, a dominant tree is constructed to depict the domination relationship within the control flow graphs. Each node in the dominant tree corresponds to the node in control flow graph, where the associated between the nodes is determined based on the domination relationship in the control flow graph. In CFG, all paths, for example, in CFG, all paths from the root node 0 to the node 7 pass through the node 1. Therefore, node 1 is dominate node 7. Similarly, it can be observed that the domination relationship is entirely based on the corresponding relationship in the control flow graph. In the graph series, the centrality of the node is often considered a key factor in understanding the graph, but this aspect can be easily overlooked in the traditional transformer self-attention mechanism. We adopt the domination number as a measure of the centrality. The number of the other nodes dominated by a node as served as creation of assess the complexity and importance of the node in the control flow. If a node dominates many other nodes, it may indicate that the node play a key role in the control flows, such as the entrance of a loop or the start point of the condition branch. The graph marks the number of nodes dominated by each node. It can be seen from the control flow graph that the more nodes a node dominate, the greater is important. There are some of the key nodes. Spatial encode is used to capture the relative position relationship between the nodes in the graph, aimed to understand the topologic relationship of nodes in non-Euclidean space. The encoding stage involved calculating the shortest path distance between the two nodes in the computation graph. The basic and based on this distance, assign a unique learnable embedding for each pair of nodes. These vectors are then incorporated into the self-attention modules. For example, the shortest path from the node 1 to node 7 is through the nodes 1 to 7. Hierarchical encoding is used to capture the hierarchical relationship between the control flow graph. In the hierarchical encoding stage, the path length between two nodes in the dominant tree is calculated. And based on this length, a unique learnable embedding is assigned to each pair of nodes. This embedding are subsequently integrated into the attention node. The path length between the node 1 and the 7 is measured, and the distance between the node 1, 3, and 7 is considered as path 1. In the graph transformer, we incorporate the centralized encoder into the input here. We use space encoding and high accuracy encoding are added as the base term to the query key input here. In the experimental evaluation, the table shows the average test of AUC score of our method, run 5 times on each project. Overall, the average AUC score exceed 0.9 across all the test project, with the highest score reached 0.975. Among these, the performance under the instruction substituting was the most outstanding, which is since the instruction replaced primary target changes and the substitution in the code, with the minimal impact on those structures. Next, we conduct a baseline compared and found through analysis of our method SU score lead over the other 3 methods in all test scenarios. We also discovered the under control flow flattening. The performance of the GMN was worst. Control flow flattening recognized all basic block in control flow graph into a single large loop structure, significantly altered the structure of the CFG. Therefore, it was the most substantial impact on the GMN method, which rely on graph neutral network to capture the local structures of the graphs. Buggers control flow introduce additional control flow paths into the program, mainly affecting the structures compared to the other methods. Our methods respectively outperformed by 4.55%, 9.91%, and 11.29%. Since ASM tweaked doesn't use the ACU score, but instead evaluate the model use precision at 1. We compared this precision at 1 of each model. From the table of the experiment results, it is evident that our method exhibits significant advantage in all cases. GMN, which is based on the local structures, shows a considerable limitation in similarity detection under the scenario, with significant structure changes, such as buggers control flow and control flow flattening. This may be because under the structure obfuscation, increasing local structure information introduce noise into the function embedding, reduce the model's detection efficiency. At the end of the experiment, we conduct an evaluation study. Generated two variable methods named using the degree centrally as the centrality encoding and disabling hierarchical encoding. Compared to our method, the degree centrality encoding method experiment are decrease in evasive code score by 9.48% in presence of the bugger's control flow and a decrease of 9.08% under the instruction replace. Degree centrality primarily focus on a node direct neighbors and doesn't cover a node position and row in the entire network. In contrast, dominator centrality encompasses this factor and considering a node position and the row within the entire network. Efficiently measure a node bridge function or key role in information flow. Therefore, the centralized encoding we designed is more rational choice for assess the importance of not the CFG.
I think we lost your screen share.
Okay. Which one?
Okay, perfect. Thank you.
In our evaluation, the graph transformer architecture demonstrated the advantage over the GN. However, a major change faced is how to effectively series the graph structure of the binary code. In this regard, designing Unicode position encoding become a key solution. Move forward, we plan to utilize the architecture to address the fine-grained level vulnerability detecting program. Thank you.
All right, let's thank our speaker. Any audience questions?
Is any of this work being released? Are you releasing the models or anything like that?
Yes, the code is opened in the GitHub, but the first author because of his health reason, so I will offer this after the conference.
All right, very cool work. Thank you.
Other questions? So one thing I've been thinking about is with obfuscation, we're kind of in this cat and mouse game between obfuscation designers and reverse engineers, and now we're ending up with even crazier obfuscations like movefuscation and things like that that kind of destroy any semblance of the control flow graph. And I'm wondering, have you thought about the resilience of GTrans in the face of those kinds of optimizations, or maybe even other ones that might really distort the control flow graph beyond recognizability?
I think the transformer architecture is enough to discover which node is more important. You cannot change the real logic of the code function. If you use the graph transformer, the key is how to show how to series the graph structure of the binary and the position encoding. So I think the transformer can discover any offer scarce tooth. I think this is enough. Thank you.
Okay. Any other questions? All right, let's thank our speaker one more time.
Thank you.
And we are at the end of our session, so the last thing will be the Best Paper Award and our concluding remarks. All righty. Jude, do you want to announce it? Sure. So, our Best Paper Award.
Our award goes to performant, flexible, and accurate rehosting while transplantations from EPFL and Boston University. Let's congratulate our authors. So the authors include Florian from EPFL, Marcel from EPFL, Qingying from EPFL and Zhejiang University, Manuel from Boston University, and Matthias from EPFL. So here we have 2 authors on site.
Thank you very much.
Thank you very much. All right. So my student is on the back, so will help us take a picture. Awesome. Thank you.
Thank you. All right. Will you do the rest of these for your co-authors?
Yeah, I will take them to that.
Wonderful.
I do want to mention one more thing. There will be a cash award thanks to ASU's generous support, and we will contact you regarding that later. Thank you.
Very cool. Thank you very much.
All right, so we hope you enjoyed this year's workshop. We're definitely in the process of growing BAR year after year, and we have even more exciting things in store for next year's workshop at NDSS. I'm told we will be in a different venue, but you'll still be here in San Diego, so we really hope to see all of you and even more folks in the binary analysis research community to come join us for next year's workshop. And with that, we can conclude this year's BAR and look forward to raising the bar next year. Thank you so much.